down, and the sea
circle games today, so stick around. Let's see. Am I coming through? I think I'm coming through all right. Yeah. Let me know if I'm not. Yeah. Welcome to
Yes, hi.
Bitophysics. Yeah. Thank you. Welcome to Bitophysics number 91. I'll talk a little bit about what we're going to be doing today. It's kind of a mishmash of a few concepts, but motivated by several things I was thinking about recently. And yeah, thanks for being here, everybody. I think a lot of people know what we do here. This is the Scientific Discourse House, founded by Sam Tomasabi and myself. Sam's a chemist and a patent lawyer, and I'm a physicist. And we like to do rooms to bring well-established science to people who are interested in science, and who may typically kind of be interested in wow, gee whiz, new developments in science, which are all kind of cool, but are usually kind of speculative, usually also a little inaccessible mathematically. And I always think it's interesting to explore very well known topics, typically in Newtonian type style physics, but oftentimes some quantum mechanics and relativity too. Those are pretty well established things at this point, 100 years on. But things that are well established and that we understand pretty well, and to look at them in a little more detail than you usually get, which I think kind of makes it a little easier to appreciate what it is that scientists do. And that's what we do here. And I'm glad to be joined by my friends Ben and Shamash also in the guise of Logic Guy, I think, I don't know which one. He uses one of those to stream us to YouTube, and he'll say a few things about that. Let's just say quick hi to Ben, because I know he won't be here too long. It's getting to be, family time over in London, Cambridge, I should say. Hi, Ben.
John, I'm with somebody. I
Okay.
can't really join the room. Read only for about half an hour probably.
All right. Good. Well,
But
it's
I'll
good to
listen. Yeah, see you soon.
have you here anyway. And Shamash, say hi and tell us about your streaming things, and give us a couple words about Philosophy Wednesdays too.
Sure. Hello. Nice to be here. Just for everybody to know, we are being streamed live on YouTube at the moment. I'll paste the link in the chat in a minute. So this is the Scientific Discourse channel. You just type Scientific Discourse. You can find us on YouTube. I'm trying my best to have all these wonderful things that John and Sam do out there on YouTube, and yeah, more good things to come. the philosophy rooms will be are happening at the same time on Wednesdays. The house is called Philosophy Wednesdays here on Clubhouse. And yeah, we're just talking about, so the guys are more on the scientific side. John and Sam, they deal with simplifying scientific concepts for the public. In the Philosophy Wednesday house, I'm trying to attack the issue from the alternative point of view, where we look at philosophical issues, whether it is the sociology of it, whether it's the politics or the economics of the scientific community, which is the topic for next week. So if you're interested in the economy, or how is it that the politics are affecting the scientific development, have they affected it in the past, what could be done about it in the future, that will be the room for you next Wednesday, same time as this room.
Yeah, thanks, Shamash. And we're also joined on stage with hero protagonist Andy, who's one of my good friends on Clubhouse, a guy who claims not to be a scientist, but boy, is one of the best scientists I've met. Andy, thanks for being here. I don't know if you want to just say hi.
Thanks for having me. I try to be sciencey.
Yeah.
That's all I can claim.
No, Andy keeps me honest. He always brings the best critical thinking to these rooms. And then there's Benjamin. Benjamin, do you want to say hi? Oh, you're in the Matrix.
Morning, John.
There you are. Yeah. We'll hear from Benjamin more later. Many of you know Benjamin. I have a love-hate relationship with Benjamin. I'm more on the love side than on the hate side. Benjamin is a provocateur, and that's not always a bad thing. So I don't, I think most of us who know Benjamin and use some critical thinking realize that you have to run hot and cold. And if you don't know Benjamin, stick around. You'll hear more. All of you down there in the goo, you're welcome to raise your hand, bring you up on stage. If I can bring Benjamin up, I can bring anybody up. And it's always good to have people on stage to interrupt me. It's easier, it's better, especially if you do have a comment, do that, come up on stage. Because if you do it in the chat, I'm likely not to see it. Maybe somebody will bring it to my attention. But it's better to have you there. See, Brian is my friend Brian, my ex Harvey Mudd classmate. And I can't say that. Brian was a year older than I was, but at any rate,
John,
Brian,
I'm not in the Matrix anymore.
You're not.
Can I just say I put the critical in thinking?
Okay, you can say that. Yeah. Anyway, Brian, it's good to see you. You and anybody else, welcome to come up on stage. Let's get Brian up on stage. I saw David raise his hand, and then I think he left the room. So. Okay, there's Brian. Hey, Brian, how's it going?
I think I did it here. Okay.
You did it.
Just going to say hi and then retreat, but nice to be with you.
Yeah, Brian's new to Clubhouse as of a few weeks ago, so still kind of learning how to press that mic button.
We all are.
Let's go ahead and get started. We're going to talk about kind of curvy motion today is what we're really going to talk about. I've got a few motives in mind. It's driven largely by a thing that I think is really bad that physics instructors have done for a long time and still do when it comes to talking about centripetal and centrifugal force in particular. And maybe we should just go ahead and go to the first slide. If you open up the slides at the top of the room there, you'll see a Google Slides presentation as always. Oops, I just realized it's got links to the Clubhouse discussion, which it shouldn't have since that's not there yet. It must be from that's a cut and paste thing. I'm going to just kind of quickly redo that.
Do it quick, because Benjamin's going to accuse you of frauding your data.
Yeah.
What with the cut and paste?
That's right. I do cut and paste. I do copy previous things, and I just forgot to erase that. Anyway, if you refresh now, you'll see there are no links to the Clubhouse discussion or YouTube replay. So let's go on to slide 2. If you took high school physics, you may have been taught something like, quote, "There's no such thing as a centrifugal force. It's centripetal force." And this is the instructor's intent in saying this is to say that when an object moves along a curved path, in particular a circular path, the thing that's making it do so is a force directed toward the center of curvature, not away from the center of curvature. And that thing that you may think of as centrifugal force isn't a real force, so you shouldn't call it a force. And all of these things. Your sense that something is forcing you away from the center is just wrong, is the idea. And I've always taken issue not only with that, but also with the admonition that you should talk about centripetal force. I don't believe that you should, I don't think there's anything wrong with saying that there's a centrifugal force, even that it's a real force. I run hot and cold on whether or not it's, quote, real. We'll talk about that. But nothing wrong with that. And there is something wrong with talking about centripetal force. So I'm going to, probably not until the end will I explain why I don't like talking about centripetal force. But I do like talking about centripetal acceleration. So the title of this one is Centripetal Acceleration and Centrifugal Force, because I think those are good terms. And if we understand them, we'll deepen our understanding not only of circular motion, but also, amazingly enough, about general relativity. Ben's not here anymore, but he probably saw where this was going immediately, and that is where it will go as well. So we will be talking about kind of general relativistic concepts within a Newtonian context. Go ahead.
Can I provide a subtitle for your talk today?
Sure.
Well, I want to subtitle your talk, I Think, Therefore I Spin.
Well, now I'm not sure if that was more than a single entendre. I'm not sure I get it.
Do you get it? Let's see if Andy gets it. Andy, do you understand? I think, therefore I spin.
I think we'll take that at least tentatively as a no. Do you want to, well, anyway, do you want to explain that now, Benjamin? Or should we wait?
No. I'm going to put that out there for a challenge for the class to pay that attention.
I think, therefore I spin.
And figure out why that is the subtext, the subtitle of this talk. I think, therefore I spin.
Okay. All right, good. That I think might have been putting the cart before the horse, but we'll get around to that too. So let's move on to slide 3, the program for today. In today's bite, we're going to take a very general look at what happens in non-inertial motion. And that is motion in which the velocity of an object isn't constant. It's objectively not constant, regardless. Because you can go into reference frames where an object that has non-constant velocity does. For instance, if I am in a plane and I jump out of the plane and I throw a rock, I'm going to see that rock moving at constant velocity. Now, somebody else won't see it moving at constant velocity. The question is, so what's happening there? Is it moving with constant velocity or not? And the answer, well, I won't give you the answer right now, but that's an example of how a change of reference frame can change the appearance of motion. If I throw a rock while I'm falling, neglecting air resistance, that rock's just going to move away from me. If I'm falling in free space, falling in empty interplanetary space, and I throw a rock, I'm just going to see that rock moving away from me at a constant speed. And the same thing is true just simply near Earth when I jump out of an airplane, except for the effects of air resistance. So that's maybe an example of what I'm talking about there. We're going to look at the general case of non-inertial motion, and then we're going to focus in on the very special case of what's called uniform circular motion. Motion in which an object travels along a circular path at a constant speed and non-zero, indeed not even constant, acceleration. And we'll talk. We have to make a few definitions to make that make sense. So when we talk about the velocity in physics, we separate out these two concepts that have to do with velocity in a very particular way. If we're speaking carefully, when we talk about the velocity of an object, That's a vector quantity. It's not enough to say 90 kilometers per hour. If a car is traveling at 90 kilometers per hour, I've told you how fast it's going. I've literally given you its speed, but I have not told you its velocity precisely because I haven't told you what direction it's moving. Velocity is a vector quantity. It has both magnitude, the speed, and direction. So 90 kilometers per hour, 30 degrees east of north, or 110 miles per hour down would be examples of specifications of velocities. Whereas the magnitude of a velocity, just the number that says how big that vector is called the speed. It's a scalar quantity. It omits any information about the direction. So I put in there some IDs. 1 mile per minute, which is the same as 60 miles per hour, or 3 millimeters per year, which might be a geological creep along a fault or something. Those are speeds. And whereas acceleration is a vector quantity like velocity. It conveys the rate at which the velocity vector is changing. And I'm gonna give you a way of thinking about acceleration that I've never done before that I think is kind of good, a graphic way of understanding it in another slide or two here. I guess maybe the next slide. So a couple of simple observations, observable facts about the universe in which we live. There is no such thing as, quote, absolute velocity. That's a hard concept to understand, and it's not made any better, I think, by saying the thing I say next there. But this gets right at it. Objects do not have velocity. It's not a property of an object. You can't look at an object and say, that object's velocity is this thing. Velocities are always measured, always, 100% of the time, no exceptions, relative to some arbitrary reference frame. And because the reference frame is arbitrary, there's no way to say that the velocity in that reference frame is the velocity. So, and in contrast to that, objects do, and this is the remarkable thing, objects do have an acceleration. They have an absolute acceleration. The acceleration can be measured relative to some arbitrary reference frame. And when we do that, we call that coordinate acceleration. But the absolute acceleration is something that regardless of the reference frame you use to describe the acceleration of the object, the motion of the object, regardless of what you as an observer may be doing, every person who's able to do physics can look at an object and determine what its absolute acceleration is, and they will all agree on that. Indeed, it's the case that there is a device called an accelerometer that you can carry with you that will tell you what your absolute acceleration is, and you have one in your pocket right now because all smartphones are now equipped with accelerometers, and they will tell you what your absolute acceleration is. So that's how simple it is actually these days to determine that. And we'll get back to talking more about that. Let me stop there for a moment, just see if any of that raised any questions or comments. And let me welcome Sam, my colleague in the Scientific Discourse House. Sam, good to see you.
Hi, everyone. Sorry I'm late.
No problem. You were with the Procrastinati, I think, before this, weren't you?
I was, and we were discussing vaccines. So,
yeah.
So I kind of...
Being late is a badge of honor in the Procrastinati Club, I think.
Yes.
Yeah.
Yes, absolutely.
Hi, Benjamin. Go ahead.
I just, the question that raised was about vectors.
Mm-hmm.
I realized that rotation is a kind of an interesting quasi-vector. If you just think about rotation, because it's binary, it doesn't have like a Hilbert space. But then it probably does have a Hilbert space because it could be at any angle. And you could probably just flip it over to represent direction. So kind of answered it myself.
Yeah, so rotations are interesting. Just a couple quick words. It is kind of off topic, but it's a nice thing to talk about. When an object rotates, you can always identify instantaneously the axis of rotation, or you can identify its angular momentum, which may be conserved if it's isolated. And those things can be indicated by a vector-like quantity, kind of as you say. It turns out to not transform the way other vectors do. But, and we've talked about this before, what you do to determine the direction of a vector is take your right hand, wrap your fingers around in the direction of rotation, and then your thumb of your right hand will point in the direction that we assign to that vector. It's really, if you think about it, it's really the only way to assign an unambiguous direction to a rotation is to let that direction be along the axis, and then you just have to make up a convention as to which way along that axis. And we do that by deciding to use our right hand rather than our left hand. And you can experiment and see that those two hands will give you different answers. Go ahead.
Also, I thought you were right. The neo idiom should be inverted. I spin, therefore I am is probably more useful.
Okay, so we're closing in on the meaning of your alternate title. And let's welcome David to the stage. Hi, David. Did you have something to say now?
Oh, hey, no, I was actually, I thought I was on stage earlier, but I left for a minute and came back. But I was actually in a screen recording of something else and testing, doing my old software testing. And it's weird that you say you didn't see me on stage till just now. For like the
Oh,
last 8 minutes I
I'm
wasn't.
well, you unmuted, and I often, that catches my eye. I kind of have my eye on the screen, so I see
Oh,
when
that's
somebody
crazy. I just came back in the room and I didn't. Anyway, because these are weird things this glitchy app does.
Yeah,
That's
yeah,
all.
yeah. And I'm on Club Deck, so it
I didn't want to
does
interrupt you though.
different glitchy things.
I didn't mean to interrupt you. No.
No problem. Okay. All right, then let's move on to slide 4, where I'm going to look for a few moments here at the general case of motion in the guise of a race car on a Le Mans road course. So I'm showing you there a car at several instants. Imagine this car trying to get down that road as fast as possible. It's racing after all. And I've shown the car at several instances. I've shown its velocity vector and I've shown its acceleration vector at each of those places. Thing about the velocity vector to notice is that it at different points along the road, it has different lengths. Those lengths are intended at least to qualitatively capture how fast the car is going. The shorter that vector, the less fast it's going. The longer, the more fast it's going. And the direction, of course, is the direction. And the thing about cars is they tend to go in the direction they're pointed. That's the way they are moving at any given instant, even though they may be turning. And the turning is kind of gotten at by the acceleration vector. And once again, I've tried to show the acceleration vectors. The acceleration vectors are drawn in qualitatively correct directions. They may or may not capture magnitudes very well. But one thing about a race car is it's almost always accelerating at the maximum possible rate. It's either slamming on its brakes to slow down and make it around a curve, slamming on the accelerator pedal to start accelerating again down a straightaway, or turning that wheel as fast as the race driver is willing to do so to make the velocity vector change its direction. So the acceleration vector of a race car is kind of an interesting thing. It tends to always have its maximum possible value determined by how tightly the tires grip the road, and then it's either mostly turning, mostly slowing down, or mostly speeding up. And that's what's kind of captured here at these several moments. So let's look at the first moment as the car is entering that first turn. The velocity vector has already changed a little bit from what it was a moment ago. A moment ago, it was driving along that straighter part of the road coming in, but it's still kind of entering the turn. And so the driver's got the wheel turned to the right. He's trying to make the car go turn right. And he's still trying to make it slow down a little bit because the side of the road is rapidly approaching and he's really got to turn. So the acceleration vector is going to make, as I've shown there, probably a greater than 90-degree angle with the velocity vector. And let's see why that is. We'll see why it is by showing you 4 successive velocity vectors from moments leading up to that point. So at the top right there, I've got a collection of velocity vectors starting from a little bit earlier and ending maybe a little bit later, actually, starting a little bit before that moment, ending a little bit after that moment. And you'll see that the first velocity vector, which is in light blue because it was the longest to go, it's fading out. Then they get darker and darker as you go down. The first vector was pretty long and pointed kind of further upward up the page. Successive velocity vectors are getting shorter and pointing more horizontally as time goes on. And I've taken all of those vectors and moved them, because the nice thing about vectors, you can move them anywhere you want. They don't have a location, they just have a magnitude and a direction. So I've just taken those velocity vectors, moved them all so that they all have the same tail, so that I can see how the velocity vector is changing by simply watching what happens to the tip. And that red vector representing the acceleration points from the first tip to the last tip. It captures the direction in which that velocity vector is changing. It doesn't really capture, I can't really tell you much about its magnitude without doing something a little more quantitative here, but that's enough for our purposes. Hopefully you can see why it makes more than a 90-degree angle to the velocity vector, and that's directly related to the fact that the velocity vector is getting shorter while it's turning. That ends up making that angle more than 90 degrees. I'll move on to the looking at the second point, and then we will, let me just do that, and then we'll take comments if there are some in a moment. So there's a similar drawing for the car as it enters the straightaway. So the second position there, the car's not moving very fast. It wants to be moving much faster. And so the driver is now presumably slamming on the accelerator pedal, trying to speed up. And if I do the same thing, collect a bunch of velocity vectors, starting with the oldest one, which was shorter, and then getting longer and longer, but collecting them all with the same tail. It's not obvious from that drawing, but they all have the same tail, and then draw a red vector from the first tip along the line of the tips to the last tip. You'll see that the acceleration vector is now basically in the same direction as the velocity vector. The angle between them is 0, and that reflects the fact that this car isn't turning at all. It's just speeding up. So that's another example of doing the same kind of thing. And you can see if you can do the same thing for the final 2 points yourself. But I'll leave that there. I did want to make a disclaimer. This is really the kind of thing I do because I know Andy's going to be here, and Andy will call me on it. He's called me on this kind of thing many times. I am, a lot of places in this presentation, I will be referring, really kind of implicitly referring to, what do I call it there? Implicit assumption that I'm working in an inertial reference frame in Euclidean space. And I don't really want to even go into that here, but what I'm really kind of saying is that I'm thinking about space the way Newton did, and I'm working in a reference frame that is itself not accelerating when I do these analyses. I won't always say that explicitly. It should be the assumption that you make unless I say something otherwise explicitly, but it will come back to bite me at some point later on in the presentation. So let me stop there for a moment, see if there's any comments or questions. I see CM raising fictitious forces, and we will indeed. Oh, in fact, I don't think I called them fictitious forces. That's a good point. I should have added that to the list, but I will when we get to it. Go ahead, Andy.
Well, you've reminded me that the F1 movie came out today.
Oh,
And yeah, it's kind of a high budget movie on F1 racing.
yeah,
I might go sneak out this afternoon and watch it.
yeah. Do you watch the series? What's that called? Is that called F1? What is it?
Oh, the Drive to Survive thing. I don't watch that a couple years ago. I haven't watched. Anyways, I try to watch F1 races now and then, but it's a laboratory for thinking about these things.
Yeah, I watched a couple of seasons of that series, and I just somehow I don't know why it didn't grab me. It wasn't it. Well, I won't go into it. Several reasons. We can talk about that later in the chat.
It's
Maybe.
it's race car porn.
Yeah. Okay, let's move on to slide 5 then. So in here, this is going to be kind of the meatiest slide, I think, of the talk here. Talk about general trajectory kinematics. There's a lot of really interesting things you can say about this. I've shown on this slide a green trajectory. That trajectory is, when we talk about the trajectory, all we're talking about is the path that it follows, irrespective of speeds along that path. Now, the path that something follows is going to look different in different reference frames. So there's always that. And it's going to look particularly different in a kind of an unfortunate way if I'm in a reference frame that is itself accelerating. So I wouldn't want to do that. But I think it's enough said just to say, I'm going to be in a nice, normal, reference frame looking at an object moving along a trajectory. Enough said. And that green thing represents the trajectory that something is following. And I'm going to have the thing moving along it generally from left to right. I've shown one moment there with its velocity vector and its acceleration vector broken into components that we're going to talk about. And I'm also showing you a thing called the instantaneous radius of curvature of that path. So let's talk about all those things for just a few moments, really make sure we understand what's going on here. One thing you know for sure is that if an object is moving along that path, then at any instant, its velocity vector has to be what we call tangent to the path. If I draw a line, if I take that blue velocity vector and I extend it in both directions as a line, that line will be exactly parallel to the trajectory at one point. And in general, we'll just kind of kiss it at that point. The trajectory will curve away from it. That's not always the case. The trajectory could be a straight line. It could also be a little more pathological case than that. It could be instantaneously straight. But in general, the trajectory will curve away from it, so that line will just kiss the trajectory, as it does in this case. And the velocity vector has to be one way or the other along that line, because I have the object moving from left to right. It's the direction that I've shown there. And there's an acceleration vector, which in this case I'm showing. It doesn't have to be this, but I'm just telling you that the acceleration vector is in that direction. That's the light red arrow with the simple A on it. That is the acceleration vector. But it's useful to break that acceleration vector up into what are called components, two vectors that will add up to A. If I start where the object is and I go along the A perp vector, and then I take my A parallel vector and I move it up to the tip of A perp, I end up getting to the end of the acceleration vector. The acceleration vector can be thought of as the sum of those two vectors, one of which is parallel to the velocity, the instantaneous velocity, and one of which is perpendicular. And you can always do that regardless of what the acceleration vector is. You can always break it up into the perpendicular and parallel components, like I've shown there. Now, what about the radius, the instantaneous radius of curvature? That's a little harder thing. You could define that very carefully mathematically, but I'm just going to say it qualitatively. It turns out that there is one and only one circle that not only passes through the place where the object is right now, but also, at least as well as you possibly can, by some definition, it matches the trajectory for a little while. It follows the trajectory as close as any circle can. And if you think about what that definition means, so it's a circle that has to pass through the point of the where the object is right now, and it has to match the trajectory as well as possible. That necessarily means that the center of that circle will be at a point that is perpendicularly away from the velocity vector. That is to say, the thing I'm calling r instantaneous, the radius of that circle, is necessarily perpendicular to the velocity. Okay, so that's how I wanted to define that. And then I'll just say this, and then you can ask questions. A parallel, the thing I'm calling a parallel, the parallel component, tells you the rate at which the speed is changing. If a parallel is in the direction of the velocity, then the speed is getting larger. It's speeding up. If a parallel is opposite the velocity vector, then the speed is getting smaller. It's slowing down. And if a parallel is 0, then the speed isn't changing at all. It's just curving. So those are the possibilities for a parallel. The more interesting thing, and I'm not even going to go through the showing this, I can do this, it's not that hard, but I'm just going to tell you that it can be shown that the perpendicular component of the acceleration is the square of the current speed divided by that radius of the instantaneous radius of curvature of the trajectory. And that's a really useful thing, especially when we start talking about uniform circular motion. Okay, so there's a lot in that little diagram and in what I've said there, and I'll stop now to see if there's any comments or questions.
Can I?
Yeah.
So it has always bothered me that at least I couldn't accept it easily that we switch from the traditional picture of I have a fixed reference point or an origin for my system, and I'm measuring everything according to that. So there's a fictional point, we will call it O, and that be the origin, and then when the body moves away or towards it, we just measure the distance from that point. That sounds nice and easy. Whereas in your picture, it seems that you posit that the origin for our study is the body itself. And
okay, yeah, that's
kind of complicated because, well, it's not accelerating away or towards itself, right?
Right. So that's a really good comment, and I imagine that there's some confusion there that I should have addressed because that's really is central. This is what's called a coordinate system independent representation of what's going on. I don't mean for you to think of any of this as implying a coordinate system. If I wanted to describe this trajectory, the velocity, the accelerations, the instantaneous center of curvature, I could do that in a reference frame where the origin is over there at the lower left corner of the slide and the x-axis runs along the lower side and the y-axis goes up the other side. So I haven't used coordinates. I'm not actually talking about how I might, in that case, a parallel, for instance, would have a positive x component and a slight small positive y component. A perp would have a negative x component and a larger y component, etc. But I never said that. I'm just simply showing you these vectors and I'm showing you where the object is. I'm showing you where the center of curvature is. I'm showing you what the trajectory is. I don't want you to think about any coordinate system. You can, if you want, put any coordinate system you want on there. I can describe that, and the description will be different depending on the coordinate system. But I'm just showing you literally what is happening. And I'm doing that just by showing you vectors without using a coordinate system to actually describe those vectors. Does any of that help?
So then
So,
V
so
along. Oh, well, actually, it was
Yeah.
your question, Shamash. Go ahead.
Let Shamash follow up, and then we'll go to you, Andy.
no. I'm just trying to understand. So, what this is just a representation. No mathematics can be done using it. Is this what you're trying to say?
Oh, that's absolutely right. There's no mathematics that can be done here because I haven't given you any values for these things. But the thing about vectors is vectors exist independent of whatever coordinate system you might choose to express their values in. Different reference frames, you would express these vectors differently. I could choose my x-axis to be in the direction that the velocity vector is now. But then would I change my coordinate system in an instant? I wouldn't want to do that. I would want to have a fixed coordinate system that simply, at any given point, I can use to say what the velocity vector is now in terms of its x and y components, etc. But I'm not doing that. I'm just showing you these vectors, and I'm not mathematically describing them at all. Those vectors exist whether or not I have a coordinate system on the page. So I don't know. Did you want to follow up again? Should we?
Andy had a question. He can go ahead.
Maybe it'll elucidate. Yeah,
Well,
go ahead, Andy.
I was just gonna say that makes sense for everything except for the V. The V has to be measured in relation to something. So unless you're saying I'm going to pick a time where I was at 0 or something, and now I'm going to accumulate my accelerations over time, and I'm going to keep track of what my V must be. But right, like V. I mean, isn't that what you said before, that you have an absolute acceleration, but you don't? V only makes sense in a frame of reference.
Yeah. So, well, I don't say I wouldn't
like that?
want to say that. I mean, the point is just think about an actual Le Mans course, right? I could express that course in terms of north and south kinds of things and tell you what the components of the velocity are at any point. Not north and south, north and east, say, right? I could use those, and I could express the components that way. But maybe the grandstand is slanted, and I really want to do it in terms of the straightaway. So I could use different reference frames to describe the vectors, and in some reference frames, the velocity, for instance, this velocity vector would only have an x component if I chose a coordinate system such that, x was in that direction and y was in some other. But if I choose a different reference frame, it's going to have different x and y coordinates. That doesn't make the velocity vector different. It's the same velocity vector. And so all I'm doing is showing you the velocity vector at this instant. And I am kind of implicitly telling you that that velocity vector is getting bigger right now. That's because a parallel is in the same direction as the velocity vector. But I wouldn't have the choice, for instance, of showing a perp being in the other direction. There's no way an object can move along that trajectory and have anything other than a perpendicular component of its acceleration directed parallel to r instantaneous. It would have to be pointed at the center of curvature. That may not be obvious from what I've said before. But once again, I'm just, to some extent, I'm just telling you the vectors. Some of those are constraints. A perp has to be in that direction. But I'm just telling you how big it is. I'm telling you how big a parallel is. I'm telling you how big V is. And if I had drawn them differently, then that's what I would be telling you. But it doesn't matter what coordinate system you use, even though the description in that coordinate system would be different if you'd used a different coordinate system. you would be describing the same vector, and all I'm showing you on here are what those vectors are. I don't know. It's a strangely difficult concept to get across. I don't know if Ben or somebody else wants to take a stab at it. Well, Ben's tied up, but
Actually, I'm just about back with you now. Just need to catch up. Which slide are you on, John?
So we're just trying to. There's on slide 5. It's a question about how that, because it looks a little like a coordinate system. Shamash was asking, about, you say, well, I don't see a coordinate system. I guess you're saying the origin of the coordinate system is there. And I was trying to explain just the idea that all I'm doing, there's been showing up. Yeah, maybe you can, actually, they probably can't see you. Anyway, just to say that all I'm doing is showing you the vectors. I'm not, this is a coordinate free representation of what's going on just by showing you the vectors without actually mathematically describing them in terms of a coordinate system. And I think that's a kind of a hard concept to get across.
So who's got the problem with it? Shamash? Is it you, buddy? What's
Has any of this helped,
Okay.
Shamash? Maybe you want to restate.
The question,
what's the issue you have with it? Yeah.
The question is, I've used, this is called the Frenet system, by the way. So I've used this system for like 10 years of my life, and I always had a conceptual problem, which is that classically speaking, what you want to do is you want to pick an origin point on the graph and use that as your inertial Euclidean frame of reference, where, this is the fixed idealized point and everything moves relative to that point. Whereas using this trick here, and I know there must be some answer because it works, but I just cannot fathom to figure it out. You just pick the body itself as your origin, and then you say, oh, it's moving in that direction, and this is its speed, and this is its trajectory. And as the object moves, all of this moves with it. And somehow it solves the translation issue.
Let me try this, because I think this is important. On that diagram, I have shown you all those vectors with their tails at the current position of the object. But none of those vectors have a position. I could move them anywhere in the plane of that page, and they'd still be the same vector. So
yes, but if you change your origin, they wouldn't be the same vector.
No. See, that's exactly wrong. No matter where I move them on the page, they are. I mean, I'm just telling you, they are exactly the same vector. Vectors don't have, they don't have position. They only have magnitude
That's not my
and
problem.
direction.
My problem is velocity is measured relative to a certain origin. So you take the first position, you take the second position, you minus them, and then you divide over time, right?
Right. That's right.
So if you change the origin, you're changing that number.
Well, that's right. But when you take those two positions, subtract them, divide by the time, regardless of the coordinate system you use, you will get that vector. And that vector can be drawn anywhere on the page, and it's exactly the same vector.
So you're saying that velocity doesn't depend on your reference frame?
It does. Velocity absolutely depends on your reference frame.
That's and it doesn't.
No. I said just the opposite. I said velocity is always measured relative to an arbitrary reference frame. Always. It's the only way you can have a velocity. Things don't have velocities. They only have velocities relative to a reference frame. Oh, okay. So here's the thing. I do intend for you to restrict yourself to reference frames that aren't moving relative to each other. You're only going to get that velocity if you choose a reference frame. If you choose reference frames that are all at rest with respect to the first one in which you determine that velocity. You can move your reference frame anywhere you want, but it itself can't be moving relative to the first reference frame, or you will then, of course, observe a different velocity. Maybe
But
does
you
that
have
help?
to add the velocities. Yes, exactly. So you're
Right.
telling me that choosing any point on the page is the same thing as choosing the point of the body, because in your calculation, the page is moving with the body. Yeah, I
Well,
already knew that.
the way I'm thinking about it is I want you to think of the page itself as being, quote, stationary. In other words, the page really is my reference frame. Now I need a coordinate system in addition to the reference frame is the page. Now I need a coordinate system. I can choose any coordinate system I want as long as it's not moving relative to the reference frame that I've chosen. Because if it is, then you're talking about a different reference frame, not just a different coordinate system. So I can slap down an X and a Y axis anywhere on that page at any angle I want to the horizontal and vertical. And as long as it's not moving, as long as it itself isn't moving, I will calculate all of the vectors that I'm showing on those page to be exactly that. I'll get different numbers for where the object is as a function of time, but when I calculate the velocities and accelerations, I will get exactly the vectors that I've shown there, vectors that have only magnitude and direction. I don't know if that helps at all. The descriptions will be different.
It definitely does. Yeah, I got it.
Yeah. No, so maybe that's the key thing. And you're right, it's a point that was implicit in my own thinking about this. The reference frame here is the page. And now you're free to choose any coordinate system you want as long as that coordinate system isn't itself moving relative to the page. Yeah, and then you'll get everything that I'm showing here. Yeah, that was good. At least it was good for me. I don't know if it was good for any. I need a cigarette. Anybody else? Was that good for anybody else? Sorry, Vince, you're new on stage. Did you have something you wanted to say?
No, I just wanted to jump on because if I hear something, I'll just pop in and say it whenever I hear something.
Okay, good. And Andy, did any of that? How you also had kind of a similar idea?
Yeah, no, what you just said about the page. Well, it's funny because, like, I think naively, I would think the page is the coordinate system, but it's in mapping you have coordinate systems and you have datums, and you can have like the same coordinate system, but then like change the datum, and a datum is kind of like just like it's like where the zero is. It's where the starting point is. But
where
you can also
reference points are.
You can also like tilt this. Anyway, I think that's kind of what you're getting at. Yeah, cool enough.
Yeah, no, I think that's really key, and it's really a nice thing to distinguish between a reference frame, which isn't a coordinate system. A reference frame is just kind of, as I say, just this page is the reference frame, and then if I actually wanted to put numbers on those vectors, I would then have to, in addition, pick a coordinate system planted on the page and make sure it doesn't move relative to the page, which is the reference frame. That's a good way of putting it.
And can they be like totally different? Can they be like okay?
Oops, you're in the matrix.
What do you call it? Oops.
I wondered if you were going to say. Yeah, go ahead.
Could it be as different as like a cylindrical versus
right.
or not cylindrical? What's the right word? Polar. Versus rectangular or
yep.
So anything that fits on that page is like game on.
That's right, indeed, and it could even be a pair of linear axes that don't make a 90-degree angle with respect to each other. I could have the x-axis be horizontally to the right, and the y-axis make a 60-degree angle with respect to that. Right? I don't even need to use Cartesian coordinate systems. Anything that assigns numbers to every place on the page is really all I need.
Whatever makes the math easier.
Yep. Okay, well that was good. As I say, I kind of enjoyed that. Thank you, Shamash, for bringing that up and for
I have a quick question.
allowing me to think about it. Go ahead, Benjamin.
Anybody thinking about why the subtitle is I spin, therefore
I'm
I
not
am?
thinking about that,
Have
Benjamin.
any ideas? I was afraid you were.
Okay.
That's why I asked the question.
It's
Well,
got a nice ring
everybody,
to it, Benjamin.
and let's just have everybody continue to think about it. And the moment it dawns on somebody what Benjamin's got in his brain, feel free to, raise your hand, come up, put a comment in the chat, whatever. Let's move on to slide 6, where I show, I'm just showing you different possible combinations of velocity and acceleration vectors. I've got these, this is an object, there's 8 objects on the page. 8 objects on the page. I've got them arranged in a circle for one good reason, but there's nothing important about the circle. They're just 8 objects. They're all moving. Their velocity vectors are all toward the top of the page. Right, the reference frame, once again, is the page, and they're all moving toward the top of the page. But they have different acceleration vectors. And of course, they could have the acceleration vector could be in any direction. I'm just showing you 8 possible directions, just to really be very explicit about this idea of speeding up, slowing down, and curving. And so the very top one there is showing an object which has its acceleration vector in the same direction as its velocity. That's an object that's speeding up. That's all it's doing. It's just going faster. It's not curving. You can tell it's not curving because a perp is 0. It has only a parallel component of the acceleration, whereas the one at the bottom of the page has the acceleration vector opposite the velocity vector. That's an object that is slowing down. Its acceleration is opposite the velocity vector. That means if you think about those how the tips of that vector are going to change, that velocity vector are going to change, they're going to change in the downward direction. That means it's going to get shorter. The velocity vector is going to be getting shorter, and therefore that object is slowing down. Moving upward, but slowing down. The acceleration is the direction in which the velocity is changing, not the direction in which the object is moving. Okay, and then going to the side, if I look at the position all the way to the right, that's an object that has no parallel component of acceleration, has only perpendicular acceleration, and specifically, the acceleration is now to the right. And that is an object that is curving to the right. It's not speeding up. It's not slowing down because a parallel is 0. It is just curving to the right. So an object whose speed is not changing, and this is such an object. That object has an unchanging speed, but it does have an acceleration because its velocity vector is changing, and in particular, it's changing toward the right. So it's curving to the right as time goes on, whereas on the opposite side, we see one curving to the left. And then maybe just to take one other example, if you look at the one in the upper, kind of the upper right, in the orange quadrant, that's an object with a velocity vector that's, once again, of course, toward the top of the page, but now the acceleration vector is upward and to the right. And that means that it has a positive parallel component. That means it's speeding up. And it has a component, perp to the right. That means it's curving to the right. So that's an object that's speeding up and curving to the right. And you can go all the way around there. And I've organized the diagram into quadrants. Any object with an acceleration value that would be kind of placed up there in the orange quadrant, the upper right, would be an object that's speeding up and curving to the right. Maybe more speeding up than curving to the right, maybe more curving to the right than speeding up, but it's doing some of both. Whereas as you go around the quadrants, one or the other thing changes. At the upper left, we have objects that are speeding up and curving to the left. And down at the lower, we have objects that are slowing down and doing one or the other of those things. So that's a nice way just to and it's all just, notice that it's all ultimately about nothing more than the angle between the velocity vector and the acceleration vector. That's all you need to know that. Okay?
Can I just say I love that slide, and I'm going to use it
Oh, good.
I'll
Thank
give
you.
you credit when I do.
Yeah, thank you. I will say I liked it too, and I don't think I've seen that before, so I think that's a good one. And if you like that, Shamash, maybe you'll like, because I think I like the next one even
Oh, the
better.
next one is even. Oh,
So, and what I'm going to say, this is really getting at the heart of the matter for today. What we experience, and I really want to, emphasize experience, is in surprising contrast to what we feel. And so I've shown all those same 8 situations in 2 diagrams here. The one on the left is showing you, in addition to the acceleration and velocity vectors, it's showing you green vectors demonstrating what we experience in those situations, whereas the set on the right is showing you the forces that we feel. And I want to be really clear about what I mean by experience and feel. So let's just take one example to make that clear. I've circled the example. In both cases, I've circled the same specific case. Acceleration to the left, velocity upward, right? So same angle between the acceleration and velocity vectors, same directions for the acceleration velocity vectors in both of those cases. Now that represents, as we already talked about, being in a car, for instance, that is curving to the left, going around a turn to the left. And I think if you just imagine yourself sitting in the car seat, cranking that wheel over and having the car make a left turn, make it go fast enough that you really do experience something. What you will experience is being thrown to the left. You feel a leftward force, dare I say a centrifugal force. We'll get back to that later. But you feel thrown to the left. Sorry, did I say to the left? I've been meaning to say to the right. You feel thrown to the right when you are making a left turn. And now I'm saying feel. You experience being thrown to the left. And I think most of you probably have seen before, heard people say, oh, you're not really being thrown to the left. You're just trying to move along a straight line while the car is turning. And that's exactly right. But there's no question that you experience being thrown to the right somehow. That's your experience. It's only when you really stop and, as I say, get in touch with your feelings that you'll notice that what you actually feel is a force to the right, whether it be your seatbelt keeping you from moving to the left, to the what did I say? You feel a force to the left. Sorry, I think I keep getting my lefts and rights mixed up. You feel a force to the left, whether it be a seatbelt keeping you from moving to the right, whether it be just friction on the seat. Maybe you're not curving fast enough. Maybe all you need is a little friction between your butt and the seat to keep you from being thrown to the right. Whether it's that you are leaning against a door on the right side of the car, and that door, you're praying, won't pop open because it's the thing that's pushing you to the left and making you accelerate with the car to the left. Those are real forces. They're felt forces. They're forces that I can identify the thing that is pushing on me or pulling on me, if you want, if it's a seatbelt. There's something that is, I can identify the thing that is causing that force. And I can feel the seatbelt digging into my right side, or I can feel the seat, pushing on my butt, or I can feel the door against my right shoulder, or whatever. There's something pushing me, pulling me to the left so that I accelerate with the car. And so those are the felt forces. But your impression is kind of the opposite, right? You have to think a little bit to really notice that you're feeling forces in the direction of the acceleration. What you experience is a force opposite the acceleration. Okay, I think I'm done with that slide. Any comments or questions on that? And you can see
Just
that
very
that
quickly.
works for all those situations as well. Yeah, go ahead, Shamash.
Do you mean to make the vectors bigger because they have bigger magnitude, or because you wanted to emphasize them?
It was the latter. I just
All right.
wanted those to be the important things. Yep. Good question. Yep.
Well, let it
Oh,
never be said that physics does not honor one's feelings and lived experience.
that's right. We get in touch with our feelings in a big way, and we honor our experience. We spin, therefore we am, something like that.
Are
Are I don't know. Okay, let's move on to 8. So what is that all about? What is that experience thing? And here's another thing. I'm going to say this. I don't think I've ever really heard anybody put it quite as bluntly as this, and I can imagine some people having an objection. But here's, because I'm venturing into the psychological now. I'm pretty wedded to this thing I'm going to say, but we'll see what other people think. And that is that we have a really strong psychological response to being surrounded in a rigid, undeforming environment. Oops, I didn't finish that sentence. Oh, yeah, I meant to say in a rigid, undeforming environment that is itself accelerating. And so I'm just putting that in there. Accelerating. Yeah. So that's what I meant to say. We have a strong psychological response to being surrounded in a rigid, undeforming environment that is itself accelerating. Our brains tell us that the environment is motionless. It's not moving, nor changing how it moves. Right? It's not a moving environment, nor changing how it moves. Even in a plane, right? I mean, you know that the plane is moving, but if you just found yourself in a plane and you'd never been in a plane before, you'd have no idea that you were moving at 500 miles an hour. Or anything else, right? And you would know, and you would have no sense that it's accelerating until it does. Interestingly enough, something happens then. But the point is that when you're in a big, rigid, undeforming environment that is itself accelerating, our brains just tell us, no, it's too big and rigid and undeforming. It's got to be motionless. Not only motionless, but not changing its motion. Go ahead, Brendan.
Corrections in line or at the bottom of the page?
Say again?
Do you want corrections in line or at the bottom of the page? You misspoke.
I may have. I do that.
And you said that you wouldn't detect the acceleration until it starts accelerating. And what you're really referring to is a derivative of acceleration. What is that called?
Yeah, well, you're talking about what's called the jerk rate, but I'm not sure what you're saying. So say that a little more clearly.
Well, I think what you just said is that if you're in surrounded by a rigid environment that is not deforming, but under constant acceleration, you won't feel anything until it starts accelerating.
Oh, well, what I guess what I meant to say is that if you're in a rigid, if you're in a plane, what I actually said, I think, is that if you're in a plane that is just flying at 500 miles per hour and you'd never been in a plane before and you just woke up and let's suppose you got rid of the rumble and the vibrations and all those other kinds of things, you'd just say, okay, here I am. I'm in this thing. I wonder what's going on. Until that thing itself banked and turned or something. And even then, of course, if it's a skilled pilot, you might not detect it. But there is a detectable thing that happens that can't be shielded when a plane does turn. It's very minor, so it's not very detectable. So the point is that when that plane actually does turn, it begins accelerating in a different way than it already is. Oh, now I'm really getting into the weeds. And you will be able to detect that.
Well, the problem is you have like multiple frames of reference overlap, and it's going to be difficult for people to.
Yeah, the problem is that I haven't really dealt with gravity yet, and we're going to. I don't know if that's what you're alluding to, but it's not the jerk rate that I'm talking about. You can tell when you are accelerating because real forces have to come to bear to make you accelerate, and you can feel those forces.
And actually, John, that's one of the things I actually wanted to jump in on, the gravity
Mm-hmm.
issue. Are you going to deal with that later? Because
I
I
am.
did have a question generally, in general terms about, the acceleration of gravity upward and the illusion of us thinking
Yes.
that we're falling down to the earth, when in truth it's the earth accelerating upwards to us and,
Yes.
keeping it on
I
its head. So
always
you're
go
going to talk
there.
about that, yeah?
I always go there, Richard.
Great. Thanks,
And I
John.
will be.
I'll wait for
Yeah,
that.
I will be going there. Thank you. Yes. Okay. So, and as I say there, the larger that environment is, and the more devoid our visual field is of conflicting cues, the stronger that psychological response. This is the part that some people might object to, but I want to consider in sequence being in a passenger car making a turn where there is this kind of psychological effect, but it's countered by the visual cues that you have. You look out the window and you can see that the world, that you've always lived in is doing something funny, right? So the car itself must now be doing something funny. There's conflicting cues. The immediate environment you're in, you might think is not moving or accelerating. You might subconsciously think, but all these visual cues are kind of making it clear that that's not the case. So it's not a strong effect. Number two, if you're in the back of a windowless panel truck, the experience is stronger because now you've eliminated the visual cues of the outside world. When that truck makes a turn, now it's really clear there's something throwing you, there's some weird new forces all of a sudden come up to make you move in this, quote, rigid, undeforming, motionless environment. Now, you may be smart enough, you've been in cars enough to know, oh, no, this is just, I'm in a car that's going around a curve. You might know that. But the illusion is stronger because you don't have the outside world. And indeed, you can't even anticipate things as well because you can't see the outside world. So you're going to be in a lot more trouble if that panel truck is in a Le Mans course. You're not going to know what's coming next. So that makes it a little harder. What about if you're in a large rotating space station? There's a picture there that shows whole rooms with people just going about normal everyday activities, feeling just like they do on Earth. In a rotating space station. And of course, and this is obviously a case where we talk about centrifugal force. Your visual cue in that case is this whole room. The only thing you're seeing is a room, and the only thing you're feeling, the only thing you're experiencing, I keep making that mistake. The only thing you're experiencing is a downward force. That's the centrifugal force. Whereas if you are really careful about, well, wait a minute, what do I feel? The only thing you're feeling is the ground that you're, the thing that you're standing on pushing you. That's the only thing you feel. But there's a very strong impression of a force toward the thing that's, acting as the ground here. Artificial gravity. We call it artificial gravity. It's the centrifugal force. And and it is opposite the acceleration. The real forces that are acting on you are acting to make you accelerate toward the center of rotation of that space station. And you can feel them. It's just that somehow your impression is not so much of those forces. Your impression is of this force that's pushing you down toward that floor. And then finally, what about being outside on the surface of the Earth? When you're standing on the Earth, you're in the largest imaginable, rigid, undeformable environment, and you have the strongest possible psychological idea that that environment isn't moving, isn't accelerating, isn't doing anything, and your strong experience is of a downward force, even though there's nothing, no identifiable object pushing you down. The only thing you feel in that situation is the ground pushing up on your feet. So we've gone progressively to larger and larger, more conflict-free, visual conflict-free situations. And we'll kind of leave that. I want you to think about that Earth one. We are going to return to it. Richard is chomping at the bit, and so am I. We will definitely get to that. But I'm going to stop there for a moment. Shanito's new on stage. I don't know if Shanito, if you had something you wanted to ask or say. Or...
Yeah, actually, thank you for asking me. I was going to say, I've only been in the room for a few moments, but what you're talking about actually reminds me of my skydiving experience.
Oh,
And
yeah, tell us.
The initial jump, you had that feeling as if you're falling, but as you're falling after that initial jump, it didn't actually feel like I was falling. I felt like there was a giant fan in front of me just blowing air up into me, because I didn't have that comparative contrast of like if you jump off of a mountain or a bridge, like there was no like sense of direction flow, as far as, gravity goes. It was a really weird, surreal experience.
Yeah.
So, yeah.
And as long as you're not too close to the ground, you don't even really see the ground coming at you yet, right? You get a little closer to the ground, you start noticing that.
Right.
But also the thing about, there is this, when you jump off something, I haven't skydived, but I used to jump off of, 5-10 foot things into pools, etc. You know that you're free falling. You know that there's something different because your internal organs rearrange themselves in response to the lack of an upward force on your feet. That's what happens, and you can tell you're falling because of the internal rearrangement of your organs. That's the thing that gives you the first cue that you may be in trouble.
So, John, the
something to think
slightly
about.
anticlimactic thing about jumping out of a plane is that you almost instantaneously go to terminal velocity. It's just
Right.
you're doing it forward because the plane is flying. The plane's slowest speed is similar to your terminal velocity. So you start off at terminal velocity forward, and then you just rearrange to downward. So you don't get that gut-wrenching feel. If you jump out of a hot air
Good
balloon,
point.
then or you do a
point.
base jump, then you feel it. So that's what's anticlimactic, if you like, about a plane jump, is you're jumping into an
Yeah.
airstream that is already roughly terminal velocity. So
That's right. Good point. I hadn't thought about that, but I mean, I've thought about it before, but that really good point. Thanks, Ben. Okay, so let's move on to 9. So what? So what about this environment thing? So the thing is, and I guess that's why I didn't want to make the correction I did now that I realize it. I really did at the top of page 8 just want to say, when you are in a rigid, undeforming environment, your brains tell you, that's all I meant to say, your brains tell you that the environment's motionless and not accelerating. But the problem is, and this is on 9 now, so when that environment itself is accelerating, for example, the car accelerating in the rearward direction during a panic stop, right? When it's slowing down, the acceleration is opposite the velocity. Our experience is that we are the thing that's accelerating, that we are accelerating in the opposite direction to that of the environment itself. In this case, the car is accelerating in the rear direction, but our sense, because of our environment, is that we are accelerating in the forward direction. And because we have an innate understanding that things only accelerate in response to forces, we kind of psychologically construct the force that we experience. There is no thing pushing us forward, but we think we're accelerating forward, so we kind of psychologically invent a forward force. But if we pay attention to the actual physical sensations, we'll realize the only thing we literally feel is the rearward force of the seatbelt if we were smart enough to attach it before doing the panic stop. And that seatbelt is acting to make us accelerate rearward with the car so that we don't keep moving with the forward velocity that we had. So we, once again, so another case where the acceleration is as shown in the red vector there. The experienced force is opposite that acceleration. That red vector is the acceleration of the environment we're in. The experienced force is opposite that, and the felt force is in the direction of the acceleration, as it must be. The only real forces, feelable forces, have to be in the direction of the acceleration. And in this case, that is an absolute acceleration, as we'll talk about when we talk about accelerometers here. Okay, so there's one example. So how do we find a value for the experienced force? It's pretty simple. Newton's second law says that acceleration is mathematically related to force by F equals ma. And as we've seen, when our environment has an acceleration a, we experience ourselves having an acceleration minus a. So the force we experience, the F experienced, is just m times minus a, m times the experienced acceleration. And so we can find the value of a itself. We can find the value of the acceleration of the environment simply by attaching an accelerometer to the environment. I just simply take my iPhone, attach it to the car, and ask the iPhone to tell me using its internal accelerometer what is the acceleration of that car. And we're going to get to accelerometers here in a moment. How do they work? But for the moment, that's just a thing. The car has an absolute acceleration. I can just ask an accelerometer to tell me what it is. And then I can slap a negative sign on that and multiply it by my mass to get the force that I experience. And so here's a concrete example. Suppose you're in a car moving at a constant velocity of 70 miles per hour north when we observe an accident a short distance in front of us and stomp on the brakes. And let's suppose that the accelerometer in the car tells us that the horizontal component, and this is something about accelerometers, they can tell you, because it's a vector they're measuring, they can tell you the components of that vector if you want. An iPhone will if you hold it in the right orientation. And so the accelerometer, let's suppose the accelerometer in the car tells us that the horizontal component of the car's acceleration is 10 miles per hour per second. Now, no accelerometer would ever do that because those are weird units, but I wanted to express it that way just to be clear that I'm putting in a reasonable acceleration. It's not unreasonable for a car to be able to decelerate, as we usually call it, at a rate of 10 miles per hour per second. That would mean it would take 7 seconds for it to lose all 70 miles per hour of its speed. And it's not unreasonable. If it's a real panic stop, you might be able to do a little better than that. But let's say 10 miles per hour per second. And it turns out, and I'm just telling you this, but 10 miles per hour per second is 0.68 g. You may know g as the, quote, acceleration due to gravity. It's 0.68 of that thing. The 9.8 meters per second that you more commonly think of acceleration of gravity as, or 32 feet per second. 0.68 of that value turns out to be what 10 miles per hour per second is. G is about 14 or 15 miles per hour per second. So we experience a horizontal force of m times negative a. That's m times negative 0.68 g south. The acceleration is south. The experienced acceleration is negative that. Negative 0.68 g south is the same thing as positive 0.68 g north. And so the experienced force ultimately is 0.68 mg north. But when we multiply our mass times the, quote, acceleration due to gravity, we get a thing, and I don't want to really get into this deeply here, but some of you probably know. That's what we call our weight. That is the force of gravity, as it's taught in high school physics or introductory physics in general. And so that force that we experience is 68% of our weight, and it is north. That's the forward direction. We experience a force equal to 68% of our weight in the forward direction toward the front of the car during this panic stop. Okay, so there's a little math there, and I'll stop for a second, see if there's any comments or questions. All right, everybody's hungry to get on. So let's take a moment and ask, what is an accelerometer? In its simplest, an accelerometer is simply a device containing what's called a test mass or a proof mass that is attached to the frame of the device by springs or some elastic thing and nothing else. So it's pretty simple. Usually what happens, there's got to be some kind of damping mechanism in an accelerometer so the mass doesn't, this is something, it uses viscous drag to make sure that the mass doesn't simply bobble around in there, that it will settle down. When the object stops moving, the viscous forces will also vanish. So the only force acting on it is the force from the springs. And so here's an example of what would be called a one-axis accelerometer. It has a sensitive direction. There's a mass suspended attached to the frame of the accelerometer by two springs, and it's embedded in some viscous damping fluid. And if this device found itself accelerating, say, to the right, then the mass would kind of move to the left relative to the frame, and ultimately would any oscillatory motion that might be induced originally would damp out. The mass would find itself permanently displaced a little bit to the left as long as the acceleration to the right continued, with the spring on the left compressed and the spring on the right extended. As a result of that, those two springs would be exerting a net force on the mass to the right that would reflect how much it's accelerating. If that whole device was accelerating faster, the springs would have to stretch and compress more in order to provide that force. So you just simply ask how much did the mass move? What's its new orientation relative to its orientation when the device isn't accelerating? And that tells you directly what the acceleration of the device is. Now, that's not really the way accelerometers are built. These days, the accelerometer in your phone doesn't have a mass attached by springs to its frame. It uses what are called piezoelectric crystals, which are held in a device, and if the device accelerates, that induces kind of a compressive stress on the piezoelectric crystal, proportional to how much acceleration is being, how much force is required to make that piezoelectric crystal accelerate. And piezoelectric crystals have this cool property that they generate an electric field when they're compressed. And then you just measure how much voltage the piezoelectric crystal is producing. And you can do that along 3 axes and get a 3-axis accelerometer that probably, I don't know what the size of these things are now, but they're tiny little chips. One tiny little chip in your phone is literally an accelerometer, and then it just reads it out and gives it to you. Now, I've probably said some things that are wrong there because I don't really know how these things are built. Benjamin probably knows a lot more about that than I do know. Ben does too. But that's all you need to know, is that you can do this. And it's effectively the same thing as this. It's just done much more wisely with modern technology. So any questions or comments about accelerometers?
It's not that complicated. A small bridge is created, and the bridge is, of course, suspended over a surface. So you have the bridge and you have the surface and a gap in between. And the bridge has enough mass that when under acceleration, the bridge tends to either sag towards the other surface, or if the acceleration is in the inverse, it would bow upwards away from the other surface. An electrical frequency is supplied to this pair such that the capacitance of the space is measured, and it's just the nature of a capacitance is by definition the surface area with some like divided by the distance between the surface area, between the area. And so as that distance moves, the capacitance of that particular component changes, and capacitance can be measured in a resonance circuit.
Yeah, that's right. So the details of it, and there's different ways of building these things, but that's a common kind of a thing. The point is just to kind of understand physically that acceleration is absolute. It has physical consequences, and so devices can be built that take advantage of those physical consequences, like the one you were talking about, or even the one that I talked about here, which is never actually used in an accelerometer, but could be. Those physical consequences, you measure them, and they tell you what the acceleration of the device is. So you just attach that device to your environment and just read off of it what the acceleration is. It's that simple. Okay.
Look up MEMS, MEM. I'm not sure what that stands for, micro electromechanical. But the MEMS chips have gotten very cheap, and well, I guess they've always been cheap, but they've gotten quite a bit better in recent years. But they're still not nearly as good as the well, in IMU units. Good IMU units don't use MEMS. Even the best MEMS aren't as good as the something that's kind of closer to to your diagram. Although I'm not certain about how. But the good accelerometers are not MEMS. I mean, they're quite expensive.
Yeah.
A couple of other comments, John. These
Yeah,
things,
Ben, I thought.
yeah, these things obviously range in size hugely from things. Here I was talking about inertial nav units could be big, like the size of a shoebox, and the tiny little surface mount chip could be sub-millimeter. They work on lots of different ways. There's always a test mass to be found somewhere, even if it's built into the crystal like you described. You could call part of the crystal the test mass. I think that's true to say. And then down at those scales, the building challenges, I think, become things like electrostatic forces become dominant, tolerances with which you can build things, electrostatic forces within them, and the like. So I don't know, just a few comments from people I've spoken to who build these things.
Mm-hmm. Yeah. Okay. Yeah. Thank you. So let's move on to slide 12 then. Now I want to really bring it down to the special case of uniform circular motion. When an object moves around a circular path, parentheses, in an inertial reference frame in Euclidean space, you only have to do that to ward off nitpicks, valid nitpicks, I'll say. But I do want to say it anyway. When an object moves around a circular path a circular path of radius r at constant speed v, we say that it's in uniform circular motion. And referring back to the general discussion that we had on slide 5, you can see that in that special case, the parallel component, the rate at which the speed changes, is 0. And so the total acceleration, which I'm just showing as black A there, is the perpendicular component of the acceleration, which is just v squared over r, as we saw on slide 5. So there's that simple. It's that simple, right? The acceleration is perpendicular to the velocity, always directed toward the center of the circle, which is why it's called, by the way, centripetal acceleration. Oh, are those dings coming through? I think they are, aren't they? I'm going to turn that down. Oops, sorry. Okay, turn that off there. So what was I saying? Yeah, so the acceleration, the centripetal acceleration as it's called, is always directed toward the center, has a constant magnitude. Notice the acceleration itself is constantly changing its direction because it's always directed toward the center, and the object itself is at different places relative to the center. And it has a magnitude equal to the square of the speed divided by the radius of the circle. And so, simple example, the capsule that's occupied by astronauts in the, quote, centrifuge at the Manned Spacecraft Center in our Space Flight Center, I guess it's called, in Houston, follows a circular path with a radius of 15 meters, kind of in this big building, goes around this circle pretty quickly. And it can actually go faster than this, but this is kind of a typical thing. This would be enough to make most of us barf. Goes around one full circle of radius, 15 meters. That's a 50-foot radius circle. Makes one complete revolution every 3 seconds. What is the centripetal acceleration of that capsule? Well, v squared over r. You can get the velocity of the capsule by simply dividing the circumference of that circle by the time, the period of the motion. So that's, and then squaring it and then dividing by r. So if I simplify that equation, you notice I get an r squared divided by an r. So there's just one r at the end. I have 4 pi squared r divided by t squared. So I'll just stick in those numbers. 4 pi squared times 15 meters divided by 3 seconds squared gives me 65.8 meters per second squared, or 65.8 meters per second per second. That's an acceleration. Let's just stop for a moment and appreciate what that is. 65.8 meters per second means it is roughly like 200 feet per second. This is an object which gains a velocity of 200 feet per second every second if it was accelerating in a straight line. An acceleration of 200 feet per second is like, 200 feet per second is about 140 miles per hour. So that would be something going from 0 to 140 miles per hour in 1 second. And that's fast. That's a really rapid acceleration because g itself is 9.8 meters per second squared. You can do a simple division there and see that that acceleration is 6.7 g. And so you would say in this situation that you are subjecting any astronaut in that capsule to a centripetal acceleration of 6.7 g. And from what we've learned before this, you would see quickly that that means that the experienced force, the centrifugal force in this case, is going to be 6.7 g times their mass, which means 6.7 times their weight. They're going to experience a force, an outward force, 6.7 times their weight. And unless you're a trained fighter pilot, you will probably pass out if you, or at least toss your cookies, if that's maintained for any amount of time. Hey Ben, you went through some training like this. Do you know what's the greatest G-force you ever experienced?
7. I can hold 7 without
Wow.
G-pants for a while. Because I'm quite short, and the short and stumpy people are, I'm 5'8", so that helps. 5'8" and quite wide, so that helps. The really tall people have bigger trouble because of the distance between their heart and their head. Yeah, I can hold about 7 with G-pants on. People hold 9 or even 11 with pressure breathing suits. It's not a nice place to be. You're fighting for your consciousness with every breath. It's disgusting. It's not fun in any way, really. I don't have any fond memories of that stuff. I can put a video of it in the chat, but it'll take a while to upload. I don't think I've got the rights to make it public, so I'll kind of temporarily make it public and then take it because it was from a TV program. But yeah, it's all good fun. I've been in centrifuges 3 times, I think, and it's fun but unpleasant. It's only fun thinking about it beforehand and thinking back on it. At the time, it's horrible.
I think it's the case. I've never actually gone through it in detail, but I think that it's the rare human being who has ever experienced more than 2 Gs. Roller coasters, I think, rarely, if ever, do worse than that.
You slam your foot on the brake in a very grippy car. You're getting around about that.
Oh, that would have to be a pretty grippy car.
Have to be a pretty grippy car, yeah. Accelerate flat out in a Tesla Plaid or something like that. You've got, because 2.4 seconds to 60 is 1G, right? So if you're doing 1G forward acceleration, then you're doing, the square root of 2 in total, 1.41G. But if you can be doing 0 to 60 in 1.9 seconds, you're getting close to 2. It's not far off.
Yeah. Okay, so that's that. So let's talk now a little more about experienced forces, things that are called pseudo forces, things that are called inertial forces, and CM added to the list earlier. Sometimes these are called fictitious. There's things called fictitious forces. These are all, I'm going to argue, they generate a lot of needless confusion. People try to distinguish between, experienced forces is kind of my name, but people try to distinguish between pseudo forces and inertial forces and fictitious forces. They try to figure out whether they're the same, in what situations they're the same, whether they're real forces, etc. So I'm just going to tell you a few things that will make it a lot simpler. All such forces arise only in reference frames having non-zero absolute acceleration. That's when they happen. They always happen only in reference frames having a non-zero absolute acceleration. All such forces and only such forces are obtained as the product of the object's mass and the opposite of the reference frame's absolute acceleration. And that is to say, they're all the same thing. There is no difference between the 3 and now 4 categories. If I add fictitious forces, there are 4 names for the same thing. They always arise only in reference frames having non-zero absolute acceleration. All such forces are given by the mass of the object, which is really weird. The inertial mass of the object times the reference frame's absolute acceleration. And so the question is, are they real forces? Are these real forces? Should we say that there's such a thing as the centrifugal force? Is it a bad thing to call that a real force? And that, I maintain, just depends on what you want to mean by real. So I propose to look at one more example. And I think maybe we'll just move on to that. And so the example is standing in an upward accelerating environment. Standing in an upward accelerating environment. Boy, I need to do some better proofreading. I just got rid of that last word. Didn't need to be there. That's the example. Standing in an upward accelerating environment. Suppose you're in an environment that is absolutely accelerating upward at 9.8 meters per second squared. For instance, you could be in a rocket ship in intergalactic space, firing its rockets and accelerating at that rate, as an accelerometer would tell you. And so the question is, what force do you experience? That's easy. It's just your mass times the opposite of the acceleration. So you experience a force equal to your weight downward, just like you do on Earth, in fact. It's exactly your weight on the Earth, so that's what you experience. Is that an inertial force? I don't know if somebody wants to kind of read along with me here, if anybody wants to jump in. Maybe I'll just ask that question. I'll wait for 5 seconds, and if it's either too obvious or you don't know, I'll just go on and say it.
It is an inertial force.
And how do you know that?
Because the only reason it exists is let's say it's an elevator pushing me upwards. What I'm experiencing is the push of the floor of the elevator on my slow accelerating body. If my
That's
body
what you
accelerated
feel.
If my body accelerated instantly, I wouldn't notice.
Well, so I would say, that you experience in that case a downward force, right? But you're feeling an upward force.
I'm still wrapping my head around your choice of that lingo. For me, you chose the very bad words. So every time you say experience, I'm letting F equals minus MA just to remind myself what is it. But yes, that's how I know. I'm not sure if this is a proof for everybody, but it makes sense to me.
So there's a simpler way to be clear that it is an inertial force. Maybe you or somebody else wants to point out what it is.
Yeah, I have it. I cannot think of the thing that is doing it. It doesn't have an agent.
That's simpler, yeah. But if you just go back to slide 13, you'll see the simplest way possible of knowing that this is an inertial force. It's an inertial force because it depends on your mass. Only fictitious, inertial, experienced pseudo forces depend on your mass. It's the only category of force that does that. So it's an inertial force because you can see right there that it depends, it's proportional to your mass. That makes it an inertial force. So now, is it a real force? You're standing in this environment, it's absolutely accelerating upward at 9.8 meters per second squared. Is this an inertial force? Is it a real force? Is that experienced force, is it a real force? I think I've primed you probably to give an answer here. I'm kind of curious.
I want to say yes. I want to say
You
yes.
want to say yes?
It's a real force, yeah.
Okay.
For the person in the elevator, that's a real force. They have to. For like reality again is whatever you want to. Yeah, he can say, well, the whole thing is in my head and I'm hallucinating. But if you want to do any calculations, you're gonna have to include that thing in your calculation. You can't just say it's not there.
Okay, good. I think that was a good argument. I was a little surprised because I was thinking I had kind of primed everybody to say, no, that's not a real force. But I appreciate that, and I don't disagree. Anybody else want to comment one way or the other?
Could you ask the question again? I'll give it a shot.
So yeah, so we've established this force that you're experiencing is an inertial force. It is a fictitious force. It is a pseudo force. It is an experienced force. But is it a real force? That's the question. And I put real in quotes. It depends on what you want to define as real.
The answer I'm going to give to this is the subtitle of the talk, which is I spin, therefore am.
Okay. So you're getting at rotation being an absolute thing somehow with that as well? I don't know.
Making progress.
Okay. All right, good. So I don't really care what your answer to question 3 is. I thought Shamash gave a reasonable answer. I think you could make a reasonable, I think you could reasonably say that it isn't too, because it really just depends on what you mean by real force. And so I'll just leave that there. But would you change your answer to question 3 if you learned that an accelerometer placed on the ground on Earth will tell you that the ground has an absolute acceleration of 9.8 meters per second squared upward? In other words, the example that I'm giving you here could just be that, because I said, suppose you're in an environment that is absolutely accelerating upward at 9.8 meters per second squared. Well, the Earth is such an environment. The absolute acceleration of the surface of the Earth is 9.8 meters per second squared upward. So now, is that experienced downward force equal to your weight? Is that a real force or not? We call that force the gravitational force. We explicitly call that force the gravitational force. Is that a real force or not? Now, Shamash just gave an answer that he would say that is a real force. And once again, I already said that I don't disagree with his reasons for saying that. But I think some of you might have wanted to say that that's not a real force. It's a fictitious force. It's a pseudo force. Go ahead, Richard. Yeah,
isn't it? Yeah, I'm thinking right. So
it's
that's
experienced.
Kind of the question I wanted to
right
to talk about this. Right. So that's what you experience, but it's a function of the acceleration, which is the force that is actually creating that experience. So, as you
well, I
said,
wouldn't
it
want to
depends
call
on
the
what you want to operate on.
acceleration of. I think what you're saying, it's a product of the force upward on your feet. That's what.
Right.
That's what gives you the experience. Yeah.
Right.
Yeah. So once again, I mean, and we're just back in an area that I like to flog all the time, which is called the principle of equivalence, which is really kind of the fundamental starting point for general relativity. Einstein Einstein's greatest moment by his own personal proclamation was the time he realized that in free fall there is no gravity. That gravity, basically what general relativity is based on, is an understanding that the thing we call the force of gravity is a reference frame dependent thing. When you're in a frame that's accelerating upward at 9.8 meters per second squared, you experience gravity. And that's what the gravitational force is that pseudo force. It's the fictitious force that results from being in an environment as we are every day of our lives that is rigid, undeformable, enormous, has no conflicting cues, and is accelerating upward at 9.8 meters per second squared. And if that doesn't raise some more questions, I don't know what will, but I won't answer them or even lay them out right now. So let's see. I guess I had a couple of other questions there. What is your absolute acceleration when you stand on the Earth's surface is like that of the surface, right? Same as the surface, 9.8 meters per second squared upward, and what definitely real felt force is responsible for your absolute acceleration? It's the ground pushing up on your feet. If it weren't for the ground pushing up on your feet, you would not be accelerating with the surface of the Earth, 9.8 meters per second squared upward. So, and as I say, that should raise some questions, but I won't ask them. I think maybe Shamash is about to. Go ahead. Oh, was that Richard? Richard.
Yeah, that's
maybe.
me. Yeah, because I
Okay.
sure do. So in accelerating in reference to us, what is the full frame of reference for the Earth acceleration? Because if you're on the opposite side of the Earth now, right, and not only that, but the Earth itself is also rotating, as well as orbiting the sun and the entire solar system around the center of the galaxy. So I was just curious about that. Like, that's the
Yeah.
part I'm kind of struggling with. Like, what is the? Yes, I get the explanation.
That's the question. That is exactly the question I was alluding to.
Yes.
Yeah. So that's and that's a thing. If you tell flat earthers this kind of thing about this idea of gravity, they will laugh because they'll say, well, the Earth isn't getting, if that were true, right, your globe Earth would have to be getting bigger and bigger and bigger at an incredible rate over billions of years. It would have to be absolutely enormous. And of course, they're right if the Earth was doing that. But the answer to that, and this isn't a very satisfactory answer for most people, is that the difference is that in relativity, it's not Euclidean space. And what that means is that I can, so-called inertial reference frames in relativity are local frames. Right here, I am accelerating 9.8 meters per second squared upward relative to where I am on the Earth. And everybody at every other place is doing the same thing. But that doesn't mean that the places themselves are getting further apart, because the absolute acceleration right here is just different from the absolute acceleration in other places. That doesn't mean that they are moving apart. And that's the part that you really have to get deeper into general relativity to understand, that two places two places nearby can have absolute accelerations in opposite directions without those places getting further apart. That's a really hard thing to wrap your mind around, because you can't do that in Euclidean space. You can only do it in the curved space-time of relativity, and that's where I never like to go. I mean, I like it's enough to understand gravity in this frame as a pseudo force, as an experienced force, etc. You don't have to go that extra step unless somebody really insists on understanding why the Earth isn't getting bigger. Then you need to take a general relativity course.
But isn't it slightly getting bigger, like at the equator, and then getting smaller at the poles?
Not getting smaller.
Getting squashed, like, yeah.
It's not getting squashed, right? It has been squashed, and is now, it is squashed. It's not getting squashed.
So it's not a moment. So the parts on the equator now aren't experiencing the forces that existed a million years ago. That doesn't make sense.
No, I just mean to say when the language you used suggested that the shape of the Earth is changing,
Well,
and
yeah,
all I'm
very slowly,
saying,
but I guess it still is, no?
oh, well, not so much. I mean, the Earth has come to the form that it has precisely to make every place on Earth have the level land, every place on Earth perpendicular to the force of gravity. And so that does bring me to one more important thing, and that is the fact that when you measure gravity, when you use a plumb bob to measure the direction of gravity, when you use a gravimeter to measure, quote, the gravitational field strength or the acceleration due to gravity, that has centrifugal force in it. You might like to say, well, part of it is centrifugal force and part of it is gravity, the mass of the Earth pulling on you. And in a Newtonian view, that is what's going on. Part of it is centrifugal, part of it is gravity. But there's no way a gravimeter can't distinguish between centrifugal force and gravitational force because it's the same thing, right? It's an inertial force. Those two inertial forces combine to create a thing that we call the gravitational force. When we measure the gravitational force on ourselves, it is not the Newtonian gravitational force. It is the sum of all inertial forces, and that includes gravitation and centrifugal. And if we're moving,
Coriolis as
Coriolis.
well. Yeah.
Yep. Yep.
Now, John, if you would, let's take a trip to the moon and put this also back into the discussion of the forces that you experience there, right? I'm thinking into this that mass has a direct relationship here, doesn't it? Towards
Well,
the acceleration. Yeah, go ahead. Sorry.
no, I'm just not entirely sure what you're asking. So maybe.
Okay. If we are accelerating because of or being affected by the acceleration of the Earth upward, obviously on the moon your weight is different, everything's there. So this is a different force at work there, or in terms of the or is this just universal? So if I was in just outer space, not near any planet, right? Just I'll be free floating, right? With no particular acceleration in terms of any reference. And I'd feel then weightless. I'm just trying to understand, maybe in an elegant way
Yeah.
here.
Okay. Yeah. All right.
You know,
So let me make a couple comments on that. I mean,
sure.
so number one, I think I said maybe in here somewhere, in the reference frame of the International Space Station, and I really mean that, in that reference frame, there is no gravity, right? The astronauts experience weightlessness not because of some magical thing, blah, blah, blah. They experience weightlessness because there is no gravity in the International Space Station. Now, if you look at the International Space Station from Earth, you might say, and you took a Newtonian viewpoint, you would say, well, of course there's gravity in the International Space Station. It's only a couple hundred miles from the Earth. There's all sorts of gravity there. But that's because you're looking at it in a different reference frame. In the reference frame of the International Space Station, there is no fictitious force. Everything in the lab and everything in the International Space Station and the International Space Station itself, all of it has an absolute acceleration of 0. And so there is no fictitious forces going on. There's no gravitational force, because if there were, there would be a fictitious force going on. So when we say they're weightless, that's not just some kind of like trick. They really are weightless in the reference frame that they're living in. And so the same thing is true, of course, on the way to the moon. At some point, you land on the moon. Now there's a real force acting on you, and so you really are accelerating. But another thing related to what you were saying, Richard, is that, for instance, if I want to, when they go to the moon, Andy knows this. Andy's written a really cool program, by the way. Andy, you should put a link to your program. He used AI to help him write a cool little arcade game. Let's Go to the Moon program, which is pretty fun to play with. Everybody who's played with it has had some fun. When they go to the moon, when they went to the moon, when we do in the future, you go into low Earth orbit, and then at some point on kind of the back side of the Earth relative to the moon, you fire your rockets to make yourself go faster, to put yourself into an elliptical orbit around the Earth that has an apogee out there near the moon at a time when the moon is sweeping along in its orbit, and it's going to kind of meet you there, at which point you kind of become under its influence and go into orbit around it. But the orbit that thing goes on doesn't depend on its mass at all. If you want to send something to the moon, the only thing that matters is that you give it the right velocity at the right point in its low Earth orbit, so that it follows that trajectory. And any mass would follow the same trajectory. You could shoot a BB with that initial velocity. You could shoot a battleship with that initial, as long as you gave it the same initial velocity, it
Even a
would
feather.
follow the same path. Even a feather, that's right.
Probably, solar wind aside. I did have a comment on what Shamesh said at some point, just briefly.
Yeah, go ahead, Ben.
So Shamesh, when you were trying to compare like the bulging of the Earth due to its, slight plasticity in its early stages to like accelerating upwards at the surface, just bear in mind, if you accelerate at 1g, relativistic corrections aside, just for a day, you're doing like 22, you've done something like 22 million miles at the end of that day. I'll substantiate that calculation in the chat right now. So, when you're talking about an 8,000 mile diameter Earth bulging slightly in the middle, just 1g of just 1 day of accelerating at 1g gives you 22 odd million miles of distance traveled. So from a standing start. So just to put it in perspective.
And along, not exactly along the same lines, but I think it's just an interesting fact that the acceleration due to gravity on the Earth, 9.8 meters per second squared, is mathematically almost identical to the speed of light divided by 1 year. That is to say, if you accelerate in a Newtonian world, if you were to accelerate at g for 1 year, you would be moving at the speed of light. That's a really nice thing to just kind of remember if you're doing relativity, problems involving spaceships accelerating, et cetera. Because if you were to accelerate, if you did want to explore the universe, what you'd really ideally like to have would be a spacecraft that can sustain an absolute acceleration of 1g. Because if it could, you could just go about living your life just like you do on Earth. Your bones wouldn't deteriorate. You'd have the same acceleration that you do when you're standing on the surface of the Earth. It would feel great. And it turns out that in 20 or 25 years, you would be at the other side of the observable universe after 20 or 25 years. If you did that, that's another.
Now go on to calculate the amount of fuel you need to do that.
Yeah. Yeah, no, it's certainly not possible with rockets. One would have to find a different way to do it. So
John Elia is asking.
Oh yeah, sorry, and I see Jordy trying to get up here. Hold on a sec. Go ahead. Yeah, what did he ask?
Good morning. So here's my question. I was reading the other day about dark energy, right? And given that the time-space fabric is expanding at an increasing speed, right? And that every point is experiencing the same expansion simultaneously of the fabric. Is it is it correct to say that every point in space-time fabric emits dark energy simultaneously?
So you're asking questions, which I think I think I could only give you kind of different views on what the correct answer is, including right down to the question of whether dark energy is really a thing or not. There's kind of increasing thought that we may have misinterpreted some evidence. Let's be clear about the evidence for dark energy came from a study of distant supernova in distant galaxies, supernova in distant galaxies, and noticing, I can never remember which way it goes, that they are either brighter than they should be given their redshift, or dimmer than they should be, suggesting that that in years past they were moving slower than we would have thought. In an expanding universe, the expansion should slow down, and the suggestion from the supernovas was that the universe is speeding up its expansion. And so dark energy is the idea of this. You can accommodate it in the field equations by giving a positive value to the cosmological constant, as it's called, a thing that Einstein stuck in there originally to try to make it possible for the universe to be steady state, for it not to expand or contract. But so you can accommodate the thing. The evidence for it is that, but some people are beginning to think that that evidence has been misunderstood, that it's actually pointing at something else. And I'm not deep enough in it to be able to explain much more than that. People have these void theories, etc. So there's all of that. And then there's the question of, well, is this dark energy nothing more than the energy of the quantum energy of the vacuum due to vacuum fluctuations? And the problem with that is that if that's what it is, then it's way too small. The universe should have blown up, almost immediately. So there's lots of things that don't check out. And all of that is to say that I think the best answer to your question, well, so one more thing about it. I think the idea of dark energy has always been that it is something that simply comes with every cubic centimeter of space. Every cubic centimeter of space has the same amount of dark energy. So as space expands, you just get more dark energy, and then it expands faster. That's kind of the fundamental idea. But all of that is, that's really right out there on the fringes of what we know. And so the best answer to your question probably is we don't know.
Well, thank you. So I understand that dark energy is the explanation that we have come to explain the increasing speed at which the universe is expanding. Do we, and in spite of the controversy about dark energy, do we at least hold as a fact, scientifically speaking, that the universe is expanding at an increasing speed?
I think there'd be a lot of people who would say even that is it seems like an obvious thing, but that it may not be. There may be different explanations. So while I think the majority of the thought certainly has been the thought, but I think there are more and more people thinking that the truth may lie in something a little more subtle. Anyway, thanks. Good question. Jordy, you're new on stage too, I think. Did you have something to ask? Maybe Jordy's. And Vince, I see it.
Yes.
Oh yeah. Hi. Go ahead, Jordy.
Yes. Okay. Maybe I don't know if it has to do with the topic, but just one thing relating to the last question about the expansion of the universe. I just read somewhere that, crazy idea, could it be possible that the universe is rotating and therefore that will be some kind of centrifugal force or something like that?
So you're saying, is it possible that the universe is rotating? Is that what you said?
Yes.
Yeah. So so the first question when somebody says something like that is, how would you know?
Yeah, but the thing is, well, when Clark and who was the other? Leibniz had the discussion about whether two balls with a cord could be having tension between them, that would be a way to know that they are rotating even there is no reference.
Are you thinking? I guess I'm not sure. You're talking about the Hubble tension, I think, and I'm not sure if you're thinking that maybe a component of the explanation might be a centrifugal force or something. Is that where
Yeah,
you're kind of going with
yeah,
that?
yeah.
Yeah.
That's
Okay. So here's the thing, and it does come back to what I said first. Let's just suppose that the universe is rotating. How would you know? Well, okay, so maybe there's a centrifugal force. Okay, but here's what we know for sure is that rotation is absolute. Now, not on a universe scale. Let's forget about the universe for a moment. But if I have an object and I make it rotate, I can know for sure that it is rotating because, for instance, if I make an object flexible and I make it rotate, it will deform because of the centrifugal forces that act on it, like the Earth, right? One simple way to know that the Earth is rotating is just to notice that it's oblate.
yeah, but
That's a result of it. So, but what does it mean to say? What does it even mean to say that? Suppose here's the experiment. Here's the funny thing, and this gets at what's called Mach's principle. Here's the funny thing, is that when things don't rotate, that is to say, when they do not deform due to centrifugal force, they also do not rotate relative to the distant stars. Now, why should that be? Why should it be that a thing that isn't deforming due to rotation
yeah, the thing is,
is an object that isn't rotating with respect to the distant stars? Why should that be the case?
yeah, but this is what, for instance, Mach was saying when they were discussing about whether two balls rotating to
Whether
each
to
other,
what?
two spheres, yeah, tied with a cord, with a rope, and they are rotating around the center of gravity of them. The question was whether they were rotating respect to an absolute space or that made no sense at all. And the answer of Mach to that was, in fact, if there was no reference point where they were rotating to, there would be no tension in such a cord.
Yeah. No. Well, I think I'm not understanding every word. I'm sorry, Jordy.
Yeah,
The
okay, my
accent.
English is very bad, and also I'm not good.
No, your English is great. It's just
Uh,
you do have a pretty
okay, so
thick accent.
I try to explain again.
Mm-hmm.
This is because I'm reading a book about this, yeah? So there is the famous discussion between Clark and Leibniz about absolute space postulated by Newton in Newtonian physics. Okay, they were debating whether such a thing existed or not, and if it was needed in the theory to postulate an absolute space. And the main thought experiment that Newton had to defend the existence of absolute space was the case of two balls with certain mass, with a rope that unite them, and they are rotating around the center of gravity. And then the question was whether they were rotating respect to an absolute space in order to have the tension that we suppose they will have.
Right.
Mach said, look, you said correctly, yeah, the answer, but Mach's contra argument was, look, if there was the case that there was no absolute, there was nothing else in the universe, and because there is no absolute space, if the two balls were rotating, there would not be a tension in the core, because it makes no sense to say that they're rotating anyways.
Right. Yeah, exact. Thank you. I understood everything you said. And yeah, I agree with you. That really is kind of the interesting thought experiment. Suppose there really is nothing in the universe, and now you take two balls, attach them to a string and make them rotate, and there's supposed to be some tension in the string, but what does it mean to rotate if there's nothing to compare it to? That's the central point of Mach's principle. He ends up coming to the view that the zero rotation reference frame, the reference frame for rotation, is actually determined by the fact that there's stuff in the universe, right?
Well,
And that stuff determines it.
I don't know. In the book that I am reading, basically, what they are saying is that the difference is, let's forget about special relativity or general relativity and stick to Newtonian physics.
Mm-hmm.
And basically what they are saying is that the ontology of the Newtonian physics that postulates the existence of absolute space is wrong. And if we change it to an ontology where only we consider events, like in general, well, in special relativity, yeah, but without using just the ontology, instead of points in absolute space which persist in time, we have events, and then if we do the space diagrams, then we can see the difference between a rotating system and one that is not rotating without using absolute space. And okay, it's difficult to explain here, and I am not sure I understand the book also.
Well, it maybe, I don't know if you have a reference, maybe you want to put a link to in the chat in particular. But of course, the problem with Newtonian absolute space is that it necessarily comes along with absolute time and the idea that you actually can have distant simultaneity and everything. And we know for sure that that's wrong. So the Newtonian conception of space is clearly wrong. That I don't know exactly that necessarily is not quite the same thing as saying that Mach's principle is wrong. Mach's principle is kind of embedded in relativity. Einstein got a lot of his motivation from thinking about Mach's principle. But I've never quite wrapped my mind around. People write a lot about this, and it's not an area that I know very, very well. Mach's principle is kind of embedded in relativity because the expansion of space is revealed by the motion of stuff in space, the perceived motion of stuff in space. So it's kind of in there. But on the other hand, Mach would have said in his time that what if the universe is rotating? Well, of course, if the universe is in any sense really rotating, then distant stuff has to move at arbitrarily large velocities. And that's not a relativistic thing. So there's some tension between Mach's principle and relativity, and ultimately, just to get back to the original thing, the problem with kind of suggesting that the universe is rotating is kind of that I think at that point, then you would of course notice that when things aren't rotating with respect to the distant stars, you should see the same effects that you're postulating the rotation to affect. If the universe is going to be affected by its rotation, then things that aren't rotating with respect to the distant stars should also experience those effects. And that's not what we see. When things aren't rotating with respect to the distant stars, they aren't rotating. There are no rotational effects.
Yeah, okay. I mean, the rotation thing was just a curiosity.
Yeah.
You asked me to quote the.
No, that was good. I enjoyed that. If you have any references that are interesting, you could maybe put them in the chat.
Yeah. Okay. I just say this.
Yeah. Thanks, Jordy.
Okay. Thank you. Okay.
Yeah. So let's see. We still haven't heard Benjamin's final exposition, but I think Andy, did I see you just unmute for a moment?
I was just going to say I thought maybe the axis of evil was going to come up in that little dialogue, but
yeah, that's right. There is that too. I'm not going there if you're not. So
yeah, I'd like to hear that. I don't know if anyone wants to share
well,
that.
Well, just really, that's okay. Really briefly, one of the things that that especially religious cosmologists, anti-Big Bang. It's a funny thing. People who are opposed to the Big Bang cosmology, or really just kind of astrophysics in general, will quote this result that we know from astrophysics as evidence against astrophysics, which which is that the cosmic background radiation, the way, so we've had these satellites that have detected these minor variations in the cosmic background radiation has a kind of a fundamental temperature. It has a dipole-like asymmetry that is due to the Earth's kind of proper motion relative to, and this is where Mach's principle kind of comes back in it. There is at least one can cite the cosmic background radiation as a reference frame, and the Earth moves relative to that reference frame. A lot of people would try to say, well, that's an absolute reference frame. Well, anyway, I won't go into that. But you can certainly use that as a reference for velocity, and the Earth has a velocity relative to the reference frame in which the cosmic background radiation is uniform, and we know what direction we're moving because the cosmic microwave background is slightly warmer in one direction and colder in the opposite direction. That's called the dipole moment of the radiation. You express it in mathematical terms as a dipole moment term in what's called a multipole expansion. But if you go on beyond the dipole moment to the quadrupole, the octopole, the sixteenopole, the 32opole, these different moments in the expansion of the microwave background and what's called spherical harmonics, it turns out that the amounts of the different poles are related directly to things like how much matter, how much dark matter, how much dark energy, what the Hubble constant is, a bunch of things, cosmological constants get embedded in that thing. And all of those different moments have definite axes. The dipole moment has an obvious axis that relates to the motion of the Earth. The other moments have axes too, but they're not directly related to anything as much as the dipole moment is. But yet it turns out, I think, is it that maybe you know, Andy, I can't remember. I think maybe the quadrupole and the octopole moment at least both seem to have axes that are, I think, aligned pretty closely, more closely than you would expect by random chance, with the axis of rotation of the Earth, or maybe the axis of orbital revolution around the sun. One of those things, suggesting to people who are so inclined that the Earth is special. Right? That the fact that the cosmic microwave background has these octopole and quadrupole moments that have axes that are kind of roughly aligned with, say, the spin axis of the Earth means that the Earth is a special place, and that's what they really go at with the.
I think it's more aligned with the solar plane.
What is it?
I think it's more aligned with our solar system's plane.
The orbital plane. Okay,
yeah. Which is funny because that's pretty different than the Earth's
Yeah, that's
plane.
true. That should be the spin axis if you want to make the Earth a special place, huh? Yeah. Anyway, that's in a nutshell. That's the axis of evil is a real thing. I mean, it is odd that there is this kind of rough alignment, but the axis of evil is well known because it's used by people who want to make the Earth a special place.
And is this basically this is just interpretation of theory, right? This is not the theory the theory makes sense. The axis, people calling the associating that with the creator. That's just mainly a interpretation of the theory. That's all right.
Well, I wouldn't even put it that way. There's no the axes of these multipole moment expansions are just what they are. They're just measured things, and there's no reason that we know of to expect them to be aligned in any particular direction. Their import is the magnitude of each of the terms in the multipole expansion, not the alignment axis for it. Although conceivably one could come up with those axes actually meaning something, but there's no implication attached theoretically to those orientations. It's just a weird fact that the first two or three of them seem to be kind of roughly aligned with either the solar system or something. And then these people make a big thing out of that fact. That's just an experimental fact, and they make a big thing out of it for the reasons I mentioned. And it's interesting because, of course, it's an experimental fact that they only know about because of the science that they're trying to deny. I always find that kind of an
Gathered
ironic
through
thing.
satellites in
Yeah.
space that they do not. The other thing about it is like the raw data. I've looked for this. I found descriptions of it, but the raw measurements show a huge dipole. And then you have to subtract, sort of like the proper motion of the Earth around the sun, and then you get less, and then you have to subtract like the motion of the sun through our galaxy, and then you get, so it's only after subtracting all these like huge dipoles that they're left with this like little dipole, and they're just kind of like, fuck, like we can't get rid of it, and it's still there, but I think it's pretty small by the time, but they're still bothered by it. That just to me tells me that that's how seriously they're trying to like reduce all this whatever, this motion, and the paper when that mentioned this was, I think, 2005 or 2004. So the political situation at that time, the axes of evil, the Bush had coined, was a thing.
Yeah,
So I think it
yeah.
was it was a bit of a
It was
joke.
a play. It's what
Yeah,
scientists always do. They dig their own graves when they come up with these names for things, right?
trying to be funny.
Yeah. No, the thing you said about the dipole moment, though, I don't think I'm not saying you're wrong, but I wasn't actually aware of them trying to actually account for the dipole completely. I don't think they. First of all, I know for sure it doesn't matter because trying to account for it doesn't change the quadrupole moment, the octupole moment, etc. All those things are what they are. Is that right? I think that's right. Irrespective of changing the velocity of the Earth to try to, or at least, accounting for the velocity of the Earth for the dipole moment. But I also wasn't aware that they thought they understood that dipole moment exclusively in terms of, the motion of the Earth around its orbit, the motion of the sun through the galaxy, the motion of the galaxy, etc. I think that might be wrong, but I don't know that maybe
It's
you have
totally
a sense.
possible.
Yeah. Let's see. Well, Fred, Fred, I don't think we've heard from you. If there's anybody else on stage we haven't heard from, you're welcome to unmute too. But let me just ask Fred if he has anything to add.
Oh, I kind of thought myself out of what I was going to ask, which was kind of related to indoor skydiving and
Oh, right.
inertia and weight and stuff like that. But I think Elia wants to go if she hasn't gone already. So
Oh, okay.
I
So,
would let's go. Let's go to her.
I think, did we hear from Elia? Anyway, yeah, Elia, if you, sorry, I have kind of lost track.
I've already asked my question. Thank you.
Yeah, I thought you had, but and now I am really losing track.
You know what,
Uh,
John? I mean, since we already, you see, basically three primary constituents are said to have, contributed to the creation of the universe since the Big Bang: dark energy, dark matter, and standard matter. I don't know if standard matter is the technical term for it, but since you argued the existence of dark energy in essence, which is a mere explanation or theory that explains the expansion of the universe, what is your take on the contributions or the part or how or the percentage of each one of those constituents? Because it's been said that standard matter is merely 20 or probably less than 20 of the existence. What do you think?
Yeah, so this is really, I'm out on the edge of my own. I'm not an expert in this stuff, but I'll say a couple things. I think one thing that's always important to understand is a lot of people think that dark energy and dark matter explains something, and there are theories. As I say, the dark energy thing maybe is the best. There really are kind of some ideas about what dark energy might be, or at least how it may depend on the size of the universe, etc. But other than that, I mean, primarily, dark energy is just a name we give to the observation of supernovas, right? We have these supernovas, kind of the most obvious implication of those observations seems to be that the universe is accelerating its expansion. But that's an interpretation of an observation. The observation is this kind of weird mismatch between the brightness of supernovas and their apparent distance as determined from the redshift of the galaxies that they're in. That's the observation. The observation is that when you get to high redshift galaxies, supernovas are either brighter or dimmer than they should be. I can never remember which it is. That's the observation. And we call that dark energy only because of kind of the immediate, most obvious way one might account for it, which is to say that the universe is accelerating its expansion. See, that's not what we observe. We don't observe the universe accelerating its expansion. We observe supernovas that aren't the brightness they should be. That's what we observe. And so calling it dark energy is a little weird because it gets around the fact that there's this observation we have to explain. Why do supernovas not appear as bright or appear too bright given how far that we think they are? How do we explain that? And one explanation could be that the universe is expanding too fast. That's the one that most people have glommed onto. And then you go from there to these ideas about what dark energy might be, et cetera. And dark matter is the same kind of thing. Dark matter is the observation that galaxies spin too fast given the amount of mass that we see. We look at the amount of light, we count the number of stars, essentially. We add up all the mass that we can see, and we know, given the mass of the Earth, I can tell you how long it should take a low Earth orbiting satellite to orbit the Earth. Well, given the amount of mass in a galaxy, I can tell you how long it should take stars out at the edge to make one pass around the galaxy, which means I could tell you how fast they ought to be moving, because if they're moving faster than that, they're going to fly off into space. And if they're moving slower than that, they're going to be sucked in, by gravity to the galaxy. And the observation from Doppler shifts of stars at the edges of galaxies is that they're moving too fast. They should be flying off into space. There's not enough mass in that galaxy to contain them. That's the observation. They're moving too fast. Now, some people want to explain that by saying, well, gravity doesn't work the way we think it does. I mean, it's not that there's dark matter. It's that we don't understand gravity. And that's a perfectly reasonable thing. I mean, people don't like that because they think we understand gravity. And if we do understand gravity, then there's got to be some matter that we're not seeing. But we don't know that. What we know is the observation. And the observation is that these stars at the edges of galaxies are moving faster than they should be if the mass is what we think it is, and if gravity works the way we think it does. But either of those things might be wrong. And the thing that's most likely wrong, I think most people would say, is that we are simply miscalculating the amount of matter, and there must be more matter there. Well, if there's more matter there, we're not seeing it. What shall we call it? We'll call it dark matter. But all of that stuff is already going away from the observation into explanations that are speculative. Most people think now that there is dark matter. I think there's good reasons, I think, to think even in the multipole expansion of the cosmic background radiation that I was talking about before. I think that one of the things you actually get out of that maybe is a distinction between dark matter and ordinary matter. I'm on the fringes once again of my understanding, but yeah. So that's where we are, and so my overall answer to your question is just that you have to understand that the names dark matter and dark energy really should be understood as names for two observations that don't immediately tell you that we have never seen dark matter, we've never seen dark energy, we've never even seen the universe expanding too fast. You know, none of those things we've seen. We have these observations that we can't account for yet, and that lead kind of in a natural way to those ideas. But the name should be really understood in terms of the observations from which they spring.
Well, so thank you. According to Einstein's famous equation, matter and energy are basically interchangeable. Now, based on what you said, as those two could be mere observations or explanations to observations that could be probably inaccurate in a sense, right? The composition of the universe, as estimated in different kind of sources, around 68% dark energy, 27% dark matter, 5% ordinary matter, could be a fallacy, could be completely wrong. Is this what you're saying? Or basically based on theories that could probably be improved in the future?
Yeah, once again, I guess I feel like the first thing I need to do is disclaim any the kind of expertise that I would need to really answer your question definitively. I think from my understanding, most of the people who actually do this work understand that you can't explain what we see with ordinary matter and just the standard Big Bang. So the standard model, this lambda CDM model, it just explicitly incorporates the cosmological constant lambda and CDM, cold dark matter. And it does a really good job of, explaining most everything except for this kind of Hubble tension problem and a few other things. So I think the ideas of dark energy and dark matter still seem like kind of the most plausible things, but then we don't know in dark matter. Then the question is, what is it? Is there a way to observe it directly in terms of like to create it in particle accelerators, or to see some effect of it, to have a theory that makes some predictions about its distribution that we can check out, so that we could actually say, oh well, we've got some evidence now for more than just there's more gravitation than we see. We'd like to have something that explains the properties of dark matter a little more than just to say we need more gravitating matter, so there's dark matter.
What's the difference
Excuse me.
between regular matter and dark matter?
Well, that's a really good question. It's one I've recently understood that I don't understand as well as I should, because I've always thought, sorry, excuse me for a moment. I may have to go. Yeah, hold on. I'm going to get a glass of water. Talk amongst yourselves.
From what I've understood, is apparently some entity, if you will, that does not interact with anything that we are familiar with. So it can only be assumed because of its gravitational, or the assumed gravitational effects on what's observed. So that's why that's the dark part, that we don't have any way, I guess, through the electromagnetic spectrum to determine what is there. It's only inferred. But yeah, go ahead, sir. Mm-hmm.
They both rely on time and space, or no?
Well, it's observations of the motion and the acceleration at a distance of large, because it's the effect is noted over a large space or large distances. So some of the expected calculations based on observations are showing a discrepancy that is being explained away by saying there's something we're not detecting that seems to have particularly gravitational effects. Much like the way they commonly explain is like two dancers holding hands, and two what do you call it, ice skaters. One you can see and one you can't see, and you can infer the existence of the one you can't see by the effects on the one you can see, assuming that gravity is working the same here and there. And that's one of the questions I wanted to ask you on. Has that been a consideration, that is gravity potentially different depending on where you are in the universe, right? Because we're making the assumption, of course, that it's the same everywhere.
Yeah, and there are these what are like modified Newtonian dynamics things. The idea that essentially kind of an attempt to abandon relativity at some level and substitute a kind of a non-simple inverse r squared Newtonian kind of a gravity, because you can imagine explaining the galaxy observations just by saying, well, maybe gravity is more than just GMM over r squared when r is really big, and that would explain those observations. It's not quite that simple, but things like that. But the question, sorry, whoever it was, whoever asked me about the distinction between dark matter and ordinary matter. When dark matter first came up, at least, and I don't know if this is still the case or not. I think it might not be. A lot of people just thought, well, it's dark matter. It's just black holes. It's stuff. It's literally because you look at a galaxy, you kind of count the stars in some sense. You take the total light, you figure out how many stars there are, you figure out how much matter there would be, kind of based on your knowledge of galaxies. But maybe there just really are like a lot of black holes. Maybe there's a lot of black holes, and we don't see them. That was one possibility, and it was, I think, largely ruled out because if there were that many black holes, as much matter in black holes as you'd expect, then you would constantly be seeing black holes moving in front of stars in our own galaxy and radically, screwing with the light from that star. You'd see the star brighten, maybe deflect a little bit for a moment as the black hole went in front of it. All of these effects that you'd expect to see. And those effects just weren't seen. And if there were enough black holes to account for it, the idea was that you'd have to see it. So the fact that we don't see it means that can't be it. But then on the other hand, when the LIGO Gravitational Wave Observatory came online and we started observing these mergers of, 15, 30 solar mass black holes at a rate that nobody expected. I mean, that was a real surprise. One thing we have learned from LIGO is that there are a lot of large, not galaxy central large type black holes, but 30 solar mass black holes are really big black holes. And I don't think anybody thought that they existed in the numbers that we now know they must exist to be popping off as often as they do in these mergers. And I at least know that for a while, people said, oh, maybe that's dark matter, even though supposedly we'd kind of ruled out black holes being dark matter. And I think, as far as I know, people have decided that that can't be it, even though I don't quite understand why. It does seem like there's a lot of matter in that. So and then I also don't know, somebody told me recently that there is a theoretical reason that we know that if there is more matter, it can't be ordinary matter. And that I don't understand. If anybody here does, I'd be happy to hear why that is. But somebody told me that we now know that there can't be ordinary matter in the amount that we need the dark matter to be. I don't understand why that is, but there you go. Okay. Wow, we've gone on for a while here today. I'm kind of ready to. Oh, Benjamin, we still haven't had your, big reveal. Do you want to reveal? Does anybody want to guess what Benjamin's on about?
Yeah,
Oh, Benjamin, you're in the Matrix.
if there's any last.
Yeah, you're in the
Yeah, it won't last
Matrix.
very long.
There you are. Better, I think.
It'll probably get fixed. Yeah.
Yep.
And I take any guesses before we.
Yeah, why don't you pose the question again?
So I proposed a secondary title for this lecture, which is I Spin Therefore I Am. Why do at least I think that's a great title for this talk?
Did we get at it at all with the conversation with Jordy about the? Yeah,
you did. Jordy's conversation I couldn't follow very well, so I can't comment on whether it got or didn't get. But I love the question, like whether or not the entire universe is spinning. I think that does kind of touch on it.
Okay, well, Benjamin, I think nobody's playing your game. You're just going to have to tell us.
Right. No, I'm very often alone in these things. It's lonely at the top, as they say. I've gotten used to it. So first of all, it's a Cartesian homage, right? And Cartesian gives us the Descartes gives us the
I think, therefore I am. That was the single entendre that I got.
Well, I think therefore I went. That was Descartes' perspective, right?
Mm-hmm.
And he was trying to solve the question of what is it that I can know absolutely, and what is it that's derived. And in physics,
spin is absolute.
Spin is absolute, and everything else is kind of relativistic and derived and derivative. So, therefore, spin holds this like central quality of being absolute.
And of course, there's the arrival time question. So there's that too.
You're doing me for me now.
I
but
am.
I don't have to do me now.
Yeah.
This saves a lot of work and pain and patience, I think.
Let's hear what Andy had to say.
Can't you equally say I accelerate, therefore I am? It doesn't fall off the tongue quite as well, but
yeah, I don't know. I think it was weak, Benjamin. I'm just going to say I think that's a pretty weak reveal.
So have you heard Mock's take on this? Because it gets back to Jordy's question.
Well, I think we were talking about it, but go ahead and give us your take on Mock's take on this.
Oh, did you mention Mock?
Oh, yeah.
Okay.
Yeah.
Well, in the case of spin, Mock had this theory that spin was relative to the sort of average matter of the universe.
Yep.
Which, according to Mock, would mean it would be impossible to know if the universe was spinning or not.
Well, I think more than impossible to know, it would be, and that was really more to Jordy's point too, kind of meaningless even to say, right?
If Mock is right, it's not clear though that Mock is right about this. I don't think we know why spin is absolute.
Yeah, no, I think that's fair to say too. I mean, I think it's kind of a central mystery, right? It's why is rotational velocity absolute? Velocity isn't, and linear acceleration, the rate of change of velocity, is absolute. They're kind of related things, frankly. But yeah, go ahead, Jordy. You were going to say something.
Yeah, the thing is, according to what I am reading, I don't fully understand because I'm not a physicist yet. So that's why maybe you, John. The problem is when you are thinking in terms of absolute rotation, we are thinking about it with an absolute space on our minds as a fundamental constituent of the universe. Yeah. But if we change this thinking into a four-dimensional universe where three-dimensional are space and one time, then if you draw the space diagrams of the rotating system, you see that let's say, how I say this, the world lines of everything that is not rotating, anything that is an inertial frame, are straight lines. More or less, this is the idea. Yeah, I don't fully understand, John, sorry. But more or less, the idea is, in order to get around this problem, is to change our ontology of space and change it into a space-time without need of special relativity.
Did you did you post? You didn't post a reference specifically that you were.
Yeah. This is a book of the book is Philosophy of Space and Time by Tim Maudlin.
By who?
Tim Maudlin.
Oh, how about that?
Yeah.
Full circle, Benjamin.
Yeah, this and you don't need to understand a lot of physics. It's just philosophy and some physics. The problem is I don't fully understand yet, so that's why I was hoping. Yeah.
Benjamin, you're seriously in the matrix. Got to work on your connection there.
John, another question I would like, because I heard also Lauren Krauss once said in one conference that the total energy mass balance of the universe is zero.
Yeah, I saw your question. I'm
I
not
cannot
sure if
understand that.
that's the. I think that's the same thing as saying that the curvature of the universe is zero, which has been a long-standing kind of surprise, right? I mean, the question from the Big Bang, from the very start with the Big Bang, the simple model of the Big Bang, the question is like, it's like throwing a rock up in the air. If you throw a rock up too slowly, it comes back to Earth. If you throw it too fast, it leaves the Earth and it's always moving fast. If you throw it at just the right speed, then it slows down, always approaching zero. It always eventually is moving as slow as you want, but it never comes back, right? That's the exact dividing line between something that comes back and something that goes on forever. And the universe could have been, in the just simple-minded thinking about a Big Bang, if the Big Bang was big enough, then the universe would simply always expand. If it wasn't big enough, then it would collapse at some point. And then there'd be just that perfect point where it would never come back, but it would be going just at the minimum bang needed not to come back. And I think that's the same question that you're asking, the same thing that Krauss is saying when he talks about the total energy of the universe. Negative energy means it collapses back. Positive energy means it expands forever. Zero energy is that perfect balance, just expanding, and it corresponds geometrically in the field equations to the solution of the field equations to the curvature of the cosmos being zero as opposed to positive or negative. And all the indications, or at least early on, I don't know what current thinking is on, because with dark energy and dark matter, a lot of things have changed. But the early thinking was that all the measurements seemed to show that it was just right at that perfect place. It seemed to be much closer to that perfect place than you would expect if it were just a kind of a random Big Bang that could have been any amount of bang you wanted. and so that was a lot of people thought, well, there must be a reason for that. It must be that a Big Bang has to be that way or something. Beyond that, I don't really know, but I think that's getting at what the thing that Krauss is talking about there.
John, let me ask it in this way. For my understanding, in the universe there is mass, which is positive. There is energy, which I assume in general is positive. And then there must be some value which is negative that compensates.
No, well, the negative comes from gravity. When you throw a rock that comes back to Earth, the total energy of that rock is negative. It has more negative gravitational potential energy than it has positive kinetic energy. If you throw it fast enough that it escapes, now it has positive energy. It has more kinetic energy when you throw it than the negative gravitational potential energy it has at the place you throw it from. And if you throw it at just the right speed, you give it a kinetic energy, a positive kinetic energy that's exactly equal to its negative gravitational potential energy, so that the total energy is zero. And so this, on the universe scale, it's the same idea. If the bang is big enough, then the negative gravitational potential energy, in some sense, of the universe is just balanced by the amount of kinetic energy, and then you get that zero total energy situation.
Yeah, now I understood. Yes, I understand now. Thank you.
Yeah. Okay, I'm ready to start shutting this thing down, but I do want to, go ahead, Richard.
Just a quick shout out, John. I
Mm-hmm.
invited the leadership of the Astronomy Association of Jamaica to the live. So I'm going to try and get them in the future, as well as some of the kids.
Oh, good.
So just a little shout out to
That's
them
great.
too. I'm broadening your audience, sir.
That's great. I saw your video that you posted with all the kids on the astronomy night. That was very cool. Both seeing you in action and everything else. That was nice.
Yeah, thank you.
Yeah.
I think I fixed the internet. Believe it or not, they're tearing up the streets here, and I saw the fiber car
Oh, they took out your
on the
fiber?
cable fibers. Yeah, it's been a little bit weird. But first of all, to Jordy, maybe Jordy doesn't know, but we've actually had conversations with Tim Maudlin by email that we've talked about in this room. That's kind of been fun. And the second thing is there's a kind of a strange thing about being a physicist, which is that it's really hard to identify whether one is or isn't a physicist. The string theorists have thought that they were doing physics for 50 years, and it turns out they weren't doing physics.
Oh, don't go there, Benjamin. I don't want to end this room this
Stop.
way. Okay, we can do this. We can do this in the after party. Okay.
All right. Well, let's have an after party.
All right, we will.
And you can
We'll start an
take
after
me apart
party.
for daring to criticize string theory.
Yeah, I may
I'm
stick around. I
guilty.
may not.
I'm guilty.
So final thoughts. Let's do. I'm ready. This is. I can't sit around for this long. Let's shut this thing down. Any final thoughts from anybody? I'm not going to go down the list and do a Steve Appel thing, but if anybody does, speak now or forever hold your peace.
Thanks again for putting this together and the PowerPoints and everything. It was awesome.
All right. Thanks, Fred. Thanks, Jordy.
No, please, somebody give me the way so I can join this, so I can ask some question to.
Yeah. So let's see. Do you have? I don't know if you're showing a pink ticket. You should join the Scientific Discourse House. Okay. I don't know. I don't even know what that means anymore. I think that only means that if you're a member of the Scientific Discourse House, it'll show up high in your hallway. But the main thing is you need to put a little note in your calendar to look here, 9:30 a.m. Pacific time. I don't know where you are. You sound like you may be in Northern Europe somewhere. Oh, it's Spain. Okay, of course. So yeah, 8 hours. What is that? Whatever that time is. 12:30 Eastern.
17:30 GMT. So in Spain it'll be 18:30.
Yeah. Oh, 18:30. Okay.
No, now it's 21:30 now here.
Yeah, I was thinking
21:30.
Yeah, 7:30. That's right.
So, okay,
I always get
I joined the this group.
All right, good. All right, Journey. Thanks everybody else, and I think I'm just going to play us out as I played us in today. I loved a little Joni, and I think we're going to do a little Joni on the way out too, and we'll see you next week.
Yesterday, a child came out to warn